Okay, yeah, hi, good morning. I will show you the Lola Windows system now that I wrote for Plan 9. First of all, why did I do this? What were the goals? So anyone who's ever looked into the Rio code knows that it's a bit not as fun to modify maybe. It's a bit hard to understand how things fit together, and there's all sorts of details sprinkled all over the place. I think it could be a little bit cleaner, and that was my goal, to make it cleaner. So for instance, Rio was written before lib9p existed, so it does the 9p server itself, which is not too bad, but I just want to make use of this library. Also, all the text handling in the window is quite, yeah, it just kind of gets in the way, and I wanted to move that out. So the goals were to have more readable code, more hackable code as well, to experiment with it and try out different features and see if it works or not. But I still want to be compatible with Rio, so that perhaps it could be used as a replacement as well. So that were my goals. As to the features that I have implemented right now, that's window decorations, so like the title bar thing, color schemes with using a certain mechanism of DevDraw, which I will talk about, virtual desktops, like the page kind, where you can pan around on a big virtual desktop, something FVWM implements, for instance, and tabbed windows, which is kind of a more exotic feature. Some Windows systems have it on different operating systems, but it's not quite common. But it really kind of fell out of the whole DevDraw architecture, so I just thought, okay, why try it out? Yeah, that's what happened. So I will demonstrate them, but first a little bit of the architecture. So if you read the 8.5 paper, or if you read 8.5 code, you know that the Windows system, the recursive, transparent multiplexer thing, where you have like the console, mouse, and bitblit files that essentially are represent what a screen with an attached mouse and keyboard are. You know this, of course. And this is multiplexed by 8.5 into these windows, and it's all very clean and transparent. Now, in Rio, that's actually no longer the case, because bitblit was replaced by DevDraw. And instead of each window seeing the same world, essentially, they get from the Windows system a window name, which is the name of an image in the draw device, and they then open this this image if they want to do some graphics and actually draw to the window. So this nice transparent architecture was kind of abandoned with Rio, and it's nothing really I could change, because I wanted to be compatible, and I obviously didn't want to replace DevDraw or anything. So just for just for information, pretty much. This is nothing I changed, but it's something to keep in mind, maybe. Now for the thread and channel architecture, I came up with these diagrams to kind of show what's going on. So we have these boxes are different processes, and the little boxes inside are threads from libthread, and the arrows are channels. So Rio has this main thread, the big one, and the 9p file system thread process, sorry, and just these I/O threads, and they communicate with channels into the main process. And they are handled there. But the thing is that 9p actually runs in a different process, and because of the way the scheduling is done, you have to be really careful with synchronization between the main thread and the 9p main process and 9p process. So what I do instead in Lola is that I only read the 9p messages in a separate process and then just send them over a channel to the main process. So that gives me access to, like, I can deal with windows, for instance, directly in the main process, in the 9p logic, because it runs in the main process, and all the synchronization is done by libthread, and there is no preemption. So it's a bit more comfortable to use it. There's less channel communication. I feel that channel communication, while it's nice, it can be a bit confusing to deal with. So for instance, this xfid alloc free thread that is in Rio, I don't even need that. It's just function calls. But otherwise, it's pretty similar. Every window has a thread. Every request that can potentially block has a thread, so the thread keeps that state of the blocking request. But otherwise, it's quite similar. Yeah, so that's for the architecture. Yeah, I think I'm just going to jump into the demonstration now. So I have a bunch of Lola sessions running here. And first of all, it looks a lot like Rio, but you can see my default theme has title bars. And well, let's maybe the first thing we could do is change it. So there's a command I wrote, set theme, and let's see, I have a bunch of, let's say, what did I want to do? This like kind of, oops, that I didn't want to show yet. So you can change the theme quite easily. There's also some kind of green matrix style theme. This is the first thing that I wanted to talk about, because it's also something that we kind of had, like you mentioned yesterday in your talk on Nile, the themes. So the way that this works is we do this with named images in DevDraw. So DevDraw has this image naming mechanism, so a client program and the Windows system can talk to each other. So the Windows system names an image, tells this name to the, like as a file, as part of the window file tree. You can read that image name and then get a handle to that image from DevDraw and do your own painting. And that mechanism, I thought, could be used for color schemes. So you have like tiny 1 pixel images that you name, like, I don't know, background, scroll bar, whatever. And you can open them from a program that wants to use colors, like draw something. And you can then like paint into these pictures from the set theme program, and everyone using the image will see the update. So you only have the actual color theme handling only in one place, and then everything, because it uses these shared images, will get the new colors. I don't know if that's a perfect solution, but I thought it was kind of nice. So the let's see, let's do something simple. So the file format of these color scheme files is taken more or less from Sigrid's Rio theme patch with the dev theme thing. I don't know, maybe I changed the names of the colors, but the file is very simple. And the set theme just reads the files, opens the images under these names, so these are actual image names, and then puts a color into it. One problem is, though, if you do like a nested thing, so if you start Lola again, it will have exactly the same theme. So if you maybe want to have a different, when you're logged into a different machine and you want to have like a visual distinction, You can't really do that right now because it's global to the draw device, to the display. Yeah. So, and that's also something that I wanted to have some feedback on. Like, how do people use this? How do they want to set their themes? Like, how should we organize this? Obviously, we could have a prefix that you can do with an environment variable or something like this. Anyways, that's the theming aspect. And I thought it was quite nice that DevDraw just gives you this for free, essentially. So let's see, what else do I have here? The window decorations you already saw. I can actually turn them off. So I can do something like no title and disappears. I can also make the border disappear. So if you don't like the title bar, then well, just don't use it. Let's turn the border on again. I don't need a title bar myself. I don't use one on Linux, but I want to see if it's possible, because with Rio, the way that Rio works, it's not really possible to do custom window decorations. The 4-pixel window border is very much hard-coded into libdraw as well. Actually, this is something I wanted to show. Okay, a little bit later. So I had to do some funky stuff with DevDraw to handle that. So the window border is really a convention. The window system just gives you the image, and it draws a 4-pixel border on it. And the client application that also wants to draw to the window knows that it has to subtract off 4 pixels and then draw inside. And this is done by turning the image that it gets from DevDraw to a screen, and then creating another image on that screen without the border. So I have this image, screen, image hierarchy that is done by libdraw for each program that wants to draw something. And I thought that was a bit ugly, and so essentially I chose to do that whole dance in the window system itself. The result of that is that it's done twice now, right now, with the libdraw that we have, which is a bit inefficient perhaps, but I don't know how bad it is, but we could optimize this away actually. Yeah, I want to show you the code, and when I do that, you'll see me switching desktops, which is another feature that I implemented. So I have corded menus on the background now. So I have the standard menus like this, the new stuff, and this. But with the 1-2 chord, I get this desktop selector. So I can go here, and this is the code that I wanted to show you, I think. So down here, yeah, I already have it selected. This is where, if the window is called starts with no border, if it doesn't start with no border, then we subtract the border width, which is, I don't know. I find that really ugly to put that into libdraw, and the whole dance here with a lock screen and then a lock window. I don't know. I think we could get rid of this in the no border case. I think I found one instance of this underscore screen thing, which is the screen that you built. No, it's the original image. I think it's a bit weird. I think it's used in like 1 or 2 places, maybe in syssource. So yeah, I think there is some potential to clean up libdraw a little bit. And yeah, I showed you the desktops already. And the funny thing is that once I had the virtual once I had the window decoration working with the image, like the content image and the window image sort of separated, I thought, okay, why not create multiple content images in the same window? Because I have a screen already on the window. Why not use it in the window system? So I thought, okay, you could do something like tabs then. And indeed, this is something I did. So if you do a new window and you don't drag a rectangle, but you just click an existing window, you will get a new tab in that window. So let's create a few maybe. Can also make that bigger. And let's see, let's start maybe Acme here and the cat clock. And so you can move these, you can switch between tabs. If I click this with the right button, I get this crosshair and I can move it to another window. I can also, if I put it on the background, I will get a new window. With the 1, 2, and 1, 3 chords, I can rearrange the order of the tabs. So 1, 2 moves to the left, 1, 3 moves to the right. So that's the tabbing feature. And there is also file system support for this, so you can create new tabs through the file system, and also turn on the border and titles, as you saw already. Yeah. I have another menu, since I talked about the chorded menus. So you see it up here with refresh, scroll, and title. I don't know about you, but when I start the Windows system, and sometimes I forget the -S flag, and I'm in no scroll mode, so it always stops, and every single window you have to do scroll mode, because I never do the no scroll mode. With this thing, you can just turn it on or off globally, and then new windows will have the setting. Same with the title bars. If I turn them off and I make a new window, it won't have a title bar. Just some fun stuff that I wanted to put into the menu. Refresh draws the whole thing new. It's probably, yeah, it could be useful maybe. So I think that is, did I have all the, yeah, I think that's pretty much the features that I wanted to show. So, yeah, what are the results? It was a nice deep dive into the internals of Rio and DevDraw and how you write a Windows system. Oh yeah, the text component thing I didn't mention yet. So I have, oops. If you look at the code, it's a bit much right now because I have like different themes, and I didn't show the Windows theme. I have a, so you have like, if you like Windows 2000, okay, you can have it. Oh, and the best thing we didn't see yet, where is it? Okay, let's quit this. Lola 3. Windows 3. I like Windows themes. Of course, we needed that. The hot dog stand. Yeah, so that's why I have a bit more code than is really there. But especially the text thing, which is almost 1,000 lines, which handles all the text handling in a window. I used that to, I wanted to separate that out of the Windows system and make it a more reusable thing. It currently works on just on a rune array, so it doesn't have any fancy text editor data structures. But I wrote this little text editor that I called Jot, and it uses this text component. So you can do things with it and then write and exit. There is no undo because it's so simple. But I just wanted to see how much work it would be to make use of this text component that I extracted out of Rio, essentially. So you may want to subtract this reusable stuff from the actual code. And even the first version without any extra features, which was mostly like Rio, it was like 1,000 lines shorter than our version of Rio and Ninefront. I don't know about other versions. It evolves a bit as well. So I think that's a good sign. I probably don't want to go into the code too much to show what I did, but at least for my taste, it's a bit cleaner. Like you're not. It doesn't mix levels of abstraction so much. Like when you want to do a file operation, you don't maybe want to know all the details of how UTF-8 is decoded into runes and all this stuff. And Rio is a bit, yeah, it mixes these things quite freely. And I wanted to have the ugly stuff separated out, and so that I could focus on more high-level logic. It's still quite challenging to write things well and have no bugs and so on. But I hope it's some progress. I did find some bugs on Plan 9 as well. They're fixed in Ninefront. I definitely need more testing. Like I need people to use it so we can find bugs and crashes especially. But I also want feedback to know what people would like for a Windows system, what kind of features they think would be useful. And I want to experiment myself a little bit more with it, but I also want to invite you to do that if you want. So tiling would be one option. I don't like tiling myself, but a lot of people do like it. So something like DWM or whatever people want could be tackled. Yeah, I think I didn't need as much time as I thought. So yeah, thanks. I can do some more demonstration if you want.
Right. Yeah. Please, you have.
Mm-hmm.
So I have a question about the colors of the theme. You don't have transparency. Have you considered that?
Transparency is a dev draw thing. That, like the whole backing store logic is in dev draw, and it's sort of out of scope for this Windows system because I'm just using dev draw. But of course, it would be interesting if that could be.
Supports it, so I think, doesn't it?
I don't think it supports transparent window. I mean, it supports transparency, but the whole backing store with like restoring what was behind the window, I don't think that works with transparency. No.
Does the Lola pager support different layouts than a 3x3 grid?
Yeah, it's just hard-coded, but you can put anything into the source code. I mean, it could make it some kind of option somewhere. But so far, 3x3 is what I use, but it's n by m. And by the way, you can move through the Windows system interface. You can also move in pixel units. Like you don't have to move by whole pages. It's just that this is my mouse interface.
Cool. This is very cool work. Have you done anything about border widths as targets?
About what, sorry?
Like grabbing the borders as handles and the fact that those widths are small on high DPI displays. We talked about that a bit yesterday.
No. Like I'm not on a super high DPI display, so I don't really have an issue with grabbing the borders. So I haven't really given it any thought either. What I can say is that it's not exactly compatible with Rio, because something that you can do in Rio is already press the button and then drag the mouse, and it will, as soon as it touches the edge, it will turn into resize. Yeah, only resize works that way. And this is something that I do not do because of the way that, well, because I have chording on the desktop.
Sorry, does that actually work from inside the Rio window as well?
No, then it will go into select mode.
Right.
Yeah.
Cool. Thank you.
Yep.
On the Windows theme, the handlebar as a gradient. Can you tell us more about how you did that? Because you said it was like 1 pixel flat color.
I can do that. Let's see, what is it? I call it Lola 98. Oh God, this theme. I had like, yeah, with this one. Oops, no, it's not. What's going on here? No. Why is the background still so terrible? Let me start a new draw term. Sorry. So. Okay. So the gradient. So what I do is, for each window width, I have a cached transparent image that goes from opaque to fully transparent. And then I have two colors for left and right. And so I blend them with the transparency thing for the window width. And whenever the window width changes, of course, I have to redo the gradient because DevDraw doesn't scale. But that's how I do it, yeah. But it's just, I haven't even committed this gradient thing to GitHub. So the code is on GitHub, by the way. I haven't even committed this yet. It's a bit of an experiment. But the theme file, it has, so it has the title bar to active and inactive. So that's, I think, yeah, left and right, something like that.
Very cool. Feature request. I'm wondering how easy it would be to have essentially active components, so like mouse button states, if you wanted to know what your mouse button states are for, especially like if you're doing demos, yeah, recording features like in the title bar.
And the title bar.
Or some component where it would be associated as an attribute of the window that you could like either enable or tie like a pipeline into.
Yeah, I haven't thought about it. Wasn't there some visualization from Russ for his Acme video?
I wrote one a while back that was kind of like show, but then you have to start one and then start a window that captured it.
I never looked into this. I don't know. So I mean, it comes from the mouse file. All the yeah, if you want to do it by window. Filter, yeah, it's a good question. I mean, logically, you would want to open the dev mouse file for that window and monitor what's going on, but that tells the Windows system that you want to draw to your own window, which maybe you don't want. I don't know. So
unless the title bar was its own window.
Yeah, I mean, it could be something that you could do in the Windows system. Yeah, maybe. I would say just give it a shot.
So the named image thing is great. I've read that in the DevDraw man pages probably a dozen times and always thought like, well, that's cool, but I don't know what I would ever use it for. And this is a great use. So you have this text as a separate element in the code. Did you look at Acme? Acme has a similar concept. Have you looked at those to see if they're similar? Was it designed with that in mind?
You mean the text component?
Yeah, the text, the like, in addition to the, what am I trying to say? You have a separate text like structure in the code, which Acme has something similar.
Yeah, it's not inspired at all by Acme. Okay. I did look into Acme code at some point and saw that it was quite different. So no relation to Acme, actually.
When I saw that, it made me think about the possibility of, when you have the ability to move a tab from one window to another, it made me think how nice it would be to be able to drop that into Acme as well.
Oh, yeah, moving a whole a completely different window into Acme. Okay, oof.
Yeah.
I don't know. I don't really use Acme that much, so I'm not very familiar with how it works actually with the whole file system. I looked into it a little bit, but I'm not super familiar with it. It seems like it's like crossing from one window system to another window system is sounds very difficult.
Yeah, you would really need some other mechanism for that, but it would be pretty cool.
Yeah. Yeah. So, well, I mean, I thought about the whole idea of like moving the. Well, the thing is, we have different kinds of screen multiplexing. Essentially, we have these overlapped floating windows. We have tabs, which just multiplexes the whole space, but like you can select different tabs. There's also tiling, where you like divide it up in some kind of fashion, and it would be nice if you could sort of nest those, like have one window manager for each style, like one multiplexer for each style, and then nest them whatever you like. So, for instance, you could have a tab thing on like the root screen, and have something like DWM desktops where you have like tags on the top. But then how do you move across different multiplexing systems, different window systems? So like it kind of boggles the mind what you could do, but it sounds really difficult to do it well and not get completely overwhelmed.
I mostly agree, but I actually feel like what you've done with the text component is closer than you think. If you look at the Acme one, because I looked at the Acme one when I was trying to do the font changes, because that's how Acme does it on that level. And I think we already have the text file that in the file system backing these. There would definitely need to be a new level of like separation there, but I think it's not as far off as that sounds. Might be something to look at. I don't know.
Yeah, maybe it could be. I mean, just copying the contents of a text window to Acme sounds possible, but I mean that was possible before. So I don't know.
Yeah, I was also thinking about the text and wondering if after you've refactored this code, is it possible to just have text be a widget inside of a window, or does it always have to fill the entire window?
No, that's essentially like libframe works already. You just give it some, I don't know, I think you just give it some image or a rectangle as well, and it just uses that. So, for instance, Acme does it like that, I think. If I'm not I may be mistaken, but I think it just uses different libframes all over the place on a single image, as far as I know. So that is just inherited from libframe, essentially. Libtext or the text.c file just adds, like the whole scrolling, selecting, blah blah blah, like stuff that is more than what is just visible.
So then, if it's like that, then I wondered if you could actually have instead of a title bar, have a tagline. You could just put an extra text widget across the top. It's editable.
Well, for that you could just use libframe even, because I mean the whole thing that libframe doesn't do is handle text that is not currently visible or should not be currently visible. So you have to. It's only a cache for what's visible. But in the title bar you have everything. So you don't even need anything like this. I think you could just use libframe for that already. But of course we had no title bars before, that's true. Yeah. I guess it would be an experiment that you could do. Acme like title bars. Yeah.
That sounds like something to try tomorrow.
Perhaps, yeah.
All right, and we also have a handful of questions from the internet. First of all, lots of compliments. People are really liking what you did here. So let me just scroll up to the first question, and that is about the beautiful Windows theme. The question is, do the buttons actually work?
Yeah, of course. So I can minimize, I can maximize, And before I close, I can even have tabs here as well, so it works on that theme as well, and I can close. And I did something here. Oh, that's actually, no, this doesn't have a function here. Sorry. Yeah,
All right.
they do work.
And the next question is, Sir Geoffrey is writing, I noticed you started different binaries for the Windows themes. Is that only for the different title bar, or are there other differences? Are there any thoughts to integrate this into the themes?
Good question. Right, so right now I only have one sort of visual theme compiled into the binary. It's like a set of standard functions that you have to write, and then you link it with the rest of the code, and then you get a binary with that theme. I mean, of course, you could do it differently, like with a declare a struct which is specific for that theme, and then kind of insert it into some list of themes that you could select. I didn't want to do it like that, at least at this stage, because it's more experimental, and I do like the simplicity of Plan 9 for sure, and I don't want to overload this Windows system with like theme selections, and you can really overdo Windows systems. And I wanted to like be a bit cautious there and not have it immediately selectable at runtime. But of course, it's something you could do.
All right, that's it for questions. Do you have another? All right.
We did a lot of demos over the years, like places like Google, about Plan 9, and we immediately lost people when we got to Rio. So something like this, if I were doing it again and I were trying to show people Plan 9, this is like, you know, the answer we'd have to not losing people on the first time we open a window. So I think it's great.
Oh, by the way, I didn't show, I can also set desktop backgrounds. Let's see. Sorry, just a second. I have, yeah, so the classic wave. So there is some complication with the window sizes if they're shared, but let's not talk about this yet right now. So Ori.
So what about a start menu and a Windows switch bar?
Okay, so I have this little script. It's just a modified WinWatch right now. Okay, I noticed my resolution is sort of. Yeah, something. Oh wait, sorry, no. Okay, so this is a little modified WinWatch, really. So I had to modify it because of the tabs. It should only show the current tab, and it should not show the stuff that is invisible. Okay, yeah, you can see a little bit of the window up there, so this is still visible, but now it's empty. And it's sticky as well, so there is a sticky flag for a window, so it stays on the same position no matter on like where you move on the desktop. I haven't implemented a start menu yet, but at least the taskbar is getting a bit closer.
Actually, that reminds me of a slightly more useful question, less trolly one. WinWatch right now just sits in a loop and pulls for Windows state. And there are a bunch of times when I thought it would be really nice to be able to script Rio based on window events. So things like new window popped up, window got resized, etc. Have you thought at all about an event file?
I mean, it was also on my mind when I touched WinWatch. I didn't think about it too much, but I also thought it would be nice to like integrate the Windows system a little bit more with the rest, so that you can react and script it and so on. So yeah, it could be something useful. I think what has to happen is just that you write programs that you want and then make the Windows system do the right thing.
the question just to follow up. P9P Acme does have this log meta file in its Windows file server, right? Which like blocks on reads, and basically every read suggests a text line with the event Windows open, window closed, stuff like that. So you can take a look and for inspiration.
Yeah, you have to like replicate it for all readers, which is something that the wctl file also doesn't do. I think you can just have one reader, if I'm not mistaken. There is something where you'd have to replicate to all readers, which is a bit, something that you have to build.
For the last point, this could be externalized to a multiplexer program, because there are a lot of stuff that you need multiple readers of, and I encountered the problem in Inferno as well. I wanted multiple readers for my mouse, and you can't do that, so you need to multiplex that before. Yeah,
I actually wrote something like this once before, and I think maybe someone else had, I forget. But it's a useful idea, like a general idea to multiplex.
A general kind of message multiplexer program called MQ, written by, handle Kekch, and then I think Ori's touched it since. It's used for the grid chat.
Yeah, it's been rewritten independently 3 times.
Okay.
And
right. You could use that maybe.
You said your desktops are like pixel. You could move pixel by pixel. Have you tried something like Oberon? I don't know if you know. Like you could like a kind of have an infinite canvas, and you put your windows wherever you want.
I mean, it is pretty much infinite. I'm just using DevDraw coordinates really. So when I move a desk, when I change the desktop, I just move all the windows like by one desktop. On the DevDraw.
You could move an arbitrary. Could you have like
coordinate system?
Can you move your desktop like? You see what I mean?
I mean, I forget what the message is called. But there was a message for this file where you can move like by 10 pixels or whatever. You can set any offset.
And if you want to take a look at Oberon, because it's very fun to like put all your windows like you would like on a wall, and then you can see. Look where you want to look.
You mean like an overview of the windows?
No, like
I haven't used Oberon. No,
just a very big screen, but you do not see it all at once, and then you can put all your windows side by side.
Like you zoom in, like Smalltalk, where you have these workspaces and you can like open them and you're inside. Is that what you mean?
It's just a continuous canvas, and you can see parts of it. And
okay.
We can talk about it more tomorrow if you want.
I mean, in theory, you could do it, but there's like I don't know if you imply any zooming that you can zoom out or.
It's not mandatory, like just moving.
Just moving, that should be possible. Although it's quite expensive in with DevDraw, because you have to recreate the windows all the time. So you won't have like a continuous movement, probably at least over a network. That's going to be hell. Maybe locally, I don't know.
The internet is also coming up with more questions. So there was one. Hang on. Does the icon in Lola 98 on the window title change as you open different programs?
No,
it's just
hard-coded.
And then a very nice comment. 2025 is now the year of the Plan 9 desktop. Somebody had to write that.
Finally, yes. We're taking over Linux.
And people are happy to hear Smalltalk mentioned, and I'm very happy to hear Oberon mentioned. All right, looks like that's it. So thank you very much again.
Yeah, thanks everyone.
All right, just
1, 2, 3, 1, 2, 3, 1, 2, 3. Hello, hello.
Yep, that sounds good. All right, keep on talking.
1, 2, 3, 1, 2, 3, 1, 2, 3.
Okay, more.
So, hello, I'm Gorka Guardiola, and I'm going to present some work that I'm doing with Enrique Soriano. We both are Plan 9 old-timers, but we didn't do this in Plan 9, and then we ported it to Plan 9, so let's see how it goes. So, the name of the thing I'm presenting is called Socarrat, which is actually the rice that gets singed on the pan when you do a paella. And it's really difficult to clean, and that's where the name comes from. So in this talk, when I talk about the file system, normally for any other audience, I wouldn't have to clarify it, but I'm talking about the data structures that you actually write to the disk, not the protocol that you use to export stuff or the API that you have on, to actually deal with files. Actually, I'm talking about X4 or XFAT, which will. So what we wanted to implement is a kind of worm, which is a write once, read many. This should be, if you are familiar with all dumps in Plan 9 or with any of the other file systems that provide this kind of service, it should be clear what it is. It's something that you can write but not delete after it's written. And it's good for backups, but also for logging what happens to the system. So the problem is, how do you actually guarantee that something is not deleted after, and against whom can you guarantee it? So having a worm is actually a kind of security guarantee. Especially if you have the logs where you write, whatever's going on in the system, and then you get an attacker, and the logs capture traces of the intrusion, and then the attacker at some point escalates privileges and tries to delete it. How can you actually guarantee that it's not deletable? And so we wanted to write a worm for logs, so it's specialized for append-only files, which cannot be deleted after. And there are two essential ways of providing a worm. Like one is specialized hardware, and this is how it used to be done in old-time Plan 9, where you have this uke box, this optical uke box, which can be just written, but it cannot be deleted. And there's the software way of doing it, like Fossil or any other subsequent Plan 9 file system that lets you have a kind of worm. There's a third way of doing it, which is distributed, but that's not a solution for us, because then you are moving the problem somewhere else. And I'm not going to go into blockchain, which is the first thing that people say. So this is for in case you have an intrusion. The first thing, if you are doing your logging outside, the first thing the intruder will do is run some kind of denial of service for your network, and then you won't have logs. So this is like the original worm device, which is a continuous printer, and it's still used in some contexts. It's actually a very good model of the guarantees we are going to try to provide. So you can break the printer, but what's printed is printed. And that's the main guarantees I'm going to talk about. And there are other ways of doing worms, like linear tape that only goes forward, and Duke boxes. The problem with all that is that they are either cumbersome or expensive, or they don't sell them anymore. We wanted to do this with software, but providing the guarantees of hardware. And this is the difficult part. Remember that we want to provide guarantees in the case the system is totally compromised. This is a very strong guarantee. We did a file system before called CLFS that provides tamper evidence in using cryptography. So you can actually modify the logs, but you will be able to check if they are modified. The way you can do that is essentially having keys and deleting them after signing the logs. So you have like a key stream. You can generate it with a ratchet or other ways. And you keep the keys offline, and then you keep consuming keys and signing the logs. And that's the way you can provide the guarantee that even in the total compromise of the system, the attacker cannot go backwards in time, because what's signed is already signed. And they can create logs for the future, but you have the time component where logs from the past cannot be modified without being detected. But this is not enough, because we want to provide the guarantee that what's written cannot be deleted. So that's why we built this Socarrat thing, which is a local worm device. The main constraint is that we wanted it to be able to use in any conventional machine, even any OS. So it's a device that you have to plug, and it's a worm device that you can use Windows, Linux, Plan 9, Mac OS, whatever. And in order to simplify our work, we specialized it to only append-only log files. And as an extra, we wanted it to be also tamper-evident using the work we did before. And we wanted to be very, very cheap. That's the main thing. So our original prototype was a Raspberry Pi 4, which is like $69. And the new prototype, which is USB 3, is Raxda 4C+, which is similar price. So that's So what are the guarantees that we want to provide? As I said, they are inspired in a continuous printer, so we call it the continuous printer model. So once committed, you cannot delete. You can write data, but you cannot delete it. If you have some sort of cache or anything between you and the data, you have to actually, now and then you have to write. You cannot just, so if the machine turns off or whatever, you don't lose too much, because you have to There's some kind of liveness warranties. And the most important one, once you print, you cannot delete or modify, or you cannot undo the write. So how do we do this with just software? So the main idea with this is what we call a reverse file system. So our device presents itself as a block device. So it looks like a hard disk. So when you write to the file system, you write blocks to the hard disk. And our device, actually, it's an intelligent hard disk. And what it does is it looks at the blocks as they are coming by, decodes it, and tries to understand what you are doing to the files, and then keeps separate files for the files that are interesting to you. So you write to an append-only file that writes to the block. Then you see the block, and then you deduce what you were trying to do to the file and keep a separate file. So the attacker has no operation to delete that file because they didn't create it. You can only append to it. No, this is a strange idea, but so how we did it originally in Linux, we have this Go component that serves a socket that serves a block device. We export that using USB on the go, and then we mount it, and this is the user machine. This can be completely compromised, but the attacker cannot actually access these files, which are created and appended only to by looking at the blocks as they go by to the file system image. And this actually looks much simpler than it is, because when you are updating a file system, there's no guarantee that the metadata and the data comes in order in any way. So you have to know at what point you are sure that, for example, if it's an inode-based file system, the inode and the tree under the inode are consistent enough that you can actually update the files here. So what happened is we have this working, and then Ron sent me an email. Are you coming to IWP9? And then I thought, so this thing here is a protocol called MBD, which is a protocol that appeared in BSD or Linux. I'm not sure.
Early 90s.
Yeah.
Yes, very old.
Which is for sending blocks on a wire. And I thought, if I wanted to port this to Plan 9, how difficult could it be? So if I export this part using 9p, so that's what I did. So I wrote a little part of this component that exports it as 9p with two files, a COTL file and a disk file. And then you can mount this, and like the whole thing actually is easy to port. We still have some parts to implement, so that's why it's a work in progress, because there's no USB on the go in Plan 9 yet. And CLFS is unimplemented, but that should be quite easy, because it's much simpler in Plan 9 than that in Linux, because you just have to look at the writes in 9p. That should be this is like very easy. So another thing that I didn't talk about, as it is now, the reverse file system only supports X4 and XFAT, which have different compromises. This doesn't matter, because you just create the image and export it, and you don't have to, like, the whole Socarrat doesn't have to have any other implementation of X4 or XFAT. Like the implementation is the reverse file system, and that's it. And there are different compromises on those. So I'll talk about that later. But in Plan 9, you pre-format the images somewhere else and you serve them. And So the difficult part about this is, at what point are you sure that the subtree of the file system that you care about for the file is updated enough that you can actually look at it and make sure that it's there. So this is a different problem for X4 and XFAT. And as an aside, X4 has journaling, so in order to make sure that the file system is consistent in the case of loss of power, whenever you write to the file system, you first write to the journal. And the journal is a circular log where you write the operations, and once you have updated the file system, supposedly you actually advance the log. So you keep the operations that are open so you can undo them in case of a loss of power to a state where you have a consistent state in the file system. And there are two guarantees that you can give. One is if you are journaling metadata, that in case of a loss of power, your metadata is not broken. And the other guarantee you can make is that there's no spurious data in your files. And in order to do this, you have to actually journal the metadata. And in order to do this, you have to journal the data. X4 has different modes, and they don't provide the guarantees they say they provide sometimes. So this is a little bit more complex than it looks, because they say that there's some mode where they say they have flashed the data before the metadata, but it's not there. So one interesting thing about this reverse file system thing is that you can actually check if the people are providing you with the invariants that you want, because you are on both sides of the file system. You can write to the file system and actually check what's going on in the journal. But so what we did, well, for XFAT, it's really easy. It's a very simple file system. Actually, if the people from Microsoft actually removed all the CRUD that they had, like for X32, X16, X whatever, and XFAT is actually quite cleaner. So it was very easy to implement. But then, but there you don't have a journal. They have like some transactional FAT thing that no one implements. So what we did is we had this idea that if enough time has gone by since you started writing to the disk and your file system is not completely broken, supposedly things have ended up in the place where they should be. So we just have like a coherent time window, and we wait from the first write you do to the file, we wait, and then we supposedly the tree is there, and it's actually there. So we also do another thing to try to provide these guarantees, is that we zero the disk. So there's some extra things there to try to be as coherent as possible. With X4, we actually use the journal as much as possible. So the thing with the journal is when you end up the transaction in the journal, at that point you supposedly know that you are at a coherent point in the file system. So you can actually look at the thing, at least with respect to that transaction to the files. I can't go into that much detail, but so we are doing all this, and now we are at the point where we can not only keep these separate warm files, but we can actually detect that people are doing bad things, because the attacker can actually try to modify files that shouldn't be modified at points where they shouldn't be modified, and because we are seeing all these transactions, we can have policies to. So what do you do if you detect that someone's trying to delete the start of a log that should be append only? And well, there are actually two things you can do. You can give back an IO error, and then funny things happen because some people in the chain may or may not ignore it, because there's, I mean, depends on the operating system, the USB stack, and well, you may be unlucky or not. We can actually reset the USB thing and export it again only read-only. Or we can do another thing, which is keep the things they are trying to delete around and the new writes around to audit it after. So we call this a honeypot policy. So the attacker thinks they are writing to the files or to the, and we keep a separate. We are still trying to find the balance for that. And so what we learned, it was very interesting because we had already the thing working with MBD, and then we wrote a separate transport for 9P. And so 9P is synchronous, and that means in some sense it's much simpler, and everything that we needed was semantically specified, which doesn't happen for NDB. I mean, it's the other part is that because it's synchronous, either you have a lot of operations in flight and then you waste a lot of memory to be able to do things fast, or you're slow. That's the thing. So there are compromises here that are interesting that we've been dealing with for the last, I don't know, 20 years. But in any case, it was very, very interesting porting to 9P because different ways of behaving with respect to synchronicity, different sizes, we uncovered a ton of bugs. So it was really, really useful for us because we uncovered many, many bugs. Someone yesterday said that the V9FS was very buggy. I didn't see that. I mean, it worked very, very well. There were a couple of things. So we are exporting a file, and in Linux you have to convert that into using the loop device into device. And that means that all your writes are in chunks of 4K. And I'm not sure how to undo that in Linux, but whatever. In Plan 9 is no problem. Like you can write, you can use the file as a device, and you get writes of any size. So, and the library we are using, which I can't remember the name, but it's like the most popular 9P library in Go, has a random limit in the IO unit of can't remember how much, but it was a very small limit that didn't make sense. So maybe later, if I don't know, can't remember the name of the library, but if someone knows who has written it and why there's limit, maybe we can talk about this later. And for the future, in Plan 9, maybe implement the missing pieces. The most difficult part is USB on the go, which is an interesting thing for Plan 9, maybe. One thing that we notice is that USB on the go is 3.0, USB 3.0 on the go that works is very difficult to find for some reason. I don't know. Supposedly in the future, all the ports are going to be USB on the go because of the new standard. But people randomly disable it. For example, all the ThinkPad laptops have USB on the go. Disabled for some reason. There's a hidden menu in the BIOS where you can actually enable it, but it's hidden, so you can't. I disassembled the thing and couldn't figure out how to put it to enable it again. Anyway, we could also do a reverse file system for other file systems. I don't know which ones or how, but and we have all the other ideas of doing this stackable, where you stack these things, and you can add different stuff to it, like cryptography or whatever. And so I think that was it. Was I on time? I'm not sure.
That's very good. Thank you.
So, questions?
Yeah, we got 2 or 3 minutes for questions.
I've thought about this problem myself. Have you thought about using transparency logs on the secure side?
Transparency what? Sorry?
Transparency logs.
What is that? I haven't, because I don't know what that
is. I completely agree with you that blockchains would be useless for this, and 95% of the companies that use blockchains, because they heard about it and were they thought the append-only properties were appealing, they should actually use transparency logs instead. It's just that very few people know about them and the properties.
So what's a transparency log?
It's an append-only. It's an authenticated data structure. It's append-only, and it's used to make digital signatures discoverable. So you change the trust policy from one where the digital signature accepted by a verifier is only for authenticity, to one where you the signature is also submitted to a transparency log, and you receive an inclusion proof, which is signed, and I can explain this.
So you are talking about the distributed system.
You can do it locally as well.
But so if you do it locally, so if you do it locally, you have to do it with public key cryptography.
Not necessarily.
Because where's the key? I mean, this is there is a total compromise of the system that you can.
Right, and it would be on the. I know how you could do this.
I mean, you can have a key, a secret key in some kind of trusted hardware,
right.
But that's when I say total, I mean total compromise of the system.
Yeah. Oh, no, I completely agree that you need the USB device and so on. What I'm saying is that. Well, it might take a while to explain.
Okay,
but,
we can talk after. Yeah.
Let's say this. I've been designing a transparency log for 4 years, and so yeah.
So you said you're essentially trying to figure out what is being written to the file system based on the blocks that are being sent to your device. I'm wondering how this interacts with, for example, let's just say I have a VM that has a disk image, and I'm writing to blocks in the virtual disk on the real disk. So I have, or for example, I'm an attacker and I want to fool you into filling up all your space. So I write to a file on disk and try to make it look like I'm generating file system metadata by filling a data file.
So that the simple answer there, I think, if I understood the question correctly, is, if I can find it, you can break the printer. That's not in the guarantees.
Yeah, I guess what I'm trying to figure out is more, I can generate writes to a data file that look like the writes to a file system. Is that something that you've considered?
No, you can't really, because I don't look so. I don't look at the blocks isolatedly. I have an idea of how the whole file system is. So every time I see a block write, I actually walk the whole thing. Some of it is cached because it should be modified in the future, but that's the.
Have you done a performance comparison between NBD and 9P?
Yes, a 9P is slower.
Why?
There are, so the simple and fast answer is there's no streaming in it. That's
But you can parallelize the requests.
yeah. But then you consume a lot of memory, and there are balances there where you start being slow because you don't have enough memory, and you have to wait for memory to be available. And there's a lot of stuff there that, but our first prototype actually was, so this is when you are running the tests locally on the machine. But when you are actually using USB, the first prototype was slow because we didn't know at the time the Raspberry Pi only has USB 2.0, and that's slow as hell. But now with the new machine, I got it working like a week ago, and then I had travel and exams and a lot of stuff that I had to do, so I haven't been able to measure it yet, but yeah.
So I see you were using NBD when you were setting this up with Linux as network.
But NBD and NDB, I'm very confused. So it's a protocol, yeah.
Yeah,
I don't know which one is which because my brain.
Network block device.
Yes.
So you say you switched to 9P. Did you consider something like ATA over Ethernet, which Plan 9 has support for?
No, I didn't. So. I don't know. It may be another protocol that we can support. I haven't thought about it. Yeah, could be.
All right. So one last question, and then we need to continue. The internet is asking, why don't you just use a DVD-R?
A DVD-R. Oh, so because. Well, there are multiple reasons, but how big is your DVD-R, and how many times do you have to change it, and do you want to go there and change it? And I can have like I don't know how many terabytes disk these days.
All right. With that, we will need to conclude. Thank you very much.
Oh, thank you.
because I have not a very good voice.
Yeah, you can go.
Okay, so my name is Thierry Laronde. For the people who didn't hear my name before, I will just make a quick talk about TeX on Plan 9. In fact, I will focus only on some misunderstanding. There is TeX on Plan 9 because there is a distribution now that is called Kekch, and I'm the creator of the distribution. Plan 9 is not regarding TeX second-rate citizen. Kekch is totally up-to-date with Satan. Plan 9 does not lag behind. And since Geoff has spoken yesterday, he mentioned TeX in the end of the paragraph about escaping APE, and TeX was mentioned. I will explain why APE is in the picture. This is totally the reason is very slight, in fact. And the main reason why APE is here is because Kekch is available for all VOSs, in fact. I cover Android, all the Linuxes, all the BSD, Plan 9. Windows will not be very difficult to add to that, but since Microsoft has done things so that you can directly add a Linux distribution on it, there is also TeX with Kekch on Microsoft. APE is used only for compilation because I have this wide range of OSs to deal with. So I used, in fact, POSIX.2, the userland, a subset, a very small subset of utilities, and POSIX utilities, but this is just for the compilation. In fact, and this is what Donald Knuth wanted at first, TeX is in fact using only the live C. Only the live C, and as Geoff has spoken about yesterday, I'm only using the live C with a standard C from 1989 or 1990. So I'm totally compatible, and it is available absolutely everywhere. There is one misunderstanding, and I will now talk about TeX versus ROF. TeX is an interpreter. Now it takes 8 bits. It takes lines, but it absolutely doesn't care about the end of lines. It doesn't see the end of lines. Whatever the system, whatever the end of lines, they are in fact discarded. The interpreter, in fact, does byte compiling. I will explain after what this is. What it produces is in fact layout for pages. The format generates is called DVI. This is a device-independent format. This format is then post-processed by some filter. In fact, I use only in Kekch DVI PS. So we start with DVI to end with PostScript. This will go in the future. The important thing about this, that's to be called TeX, and I use uppercase later, and I use this spelling TeX. It is because it has to be it has to pass the test. There is a torture test set by Donald Erwin Knuth. If such an engine passes the test, it can be called TeX. Now, this is the interpreter. The program that we call TeX, lower cases and Latin pronunciation, is in fact not a program by itself. It is an instance of the interpreter, but that is using the digest of a set of macro done by Knuth. Text is in fact virtex. I will explain what it is regarding this using plain text set of macro. There is byte compiling made by the TeX engine. In fact, there are two programs. There is initex and virtex. Initex take a set of macros and then dump its memory. This dump is called the digest. And when a program here is called TeX, this is in fact just the first argument of this is arc v0. In fact, this is a copy. This can be a hard copy of virtex, and this is the name of the file that is used to instruct virtex to load this digest. When I have something that is called latex, latex is not an engine. Latex is something like TeX. So in the very first version of latex, it was virtex, but since the name of the file is latex, it simply takes the digest of a latex macro. What has to be remembered is that a latex is in fact not an engine. it is a huge set of macros. So we use a first version of TeX called initect to digest the huge set of macro, because this is an interpreter. It takes a lot of time to just interpret the macros. So to speed up the things, this is a by compiling. We first digest the set of macro, then dump the memory, and in a second time, when I call latex, this is in fact just the name of a copy of Virtex. Because it is called latex, it will take the digest of the latex macro, the digest of the version by compiling to be able to process a latex file. This versus ROF. ROF is also an interpreter. It has been ported to be compatible with UTF-8. So TeX taking 8 bits, this is more than UTF, can do ROF. ROF takes lines, but it doesn't do by compiling. ROF constantly has to reread every file, everything. ROF versus TeX produces a set of pages too. ROF doesn't have a torture test. There is nothing telling what ROF has to be. In fact, the reference is the user manual and what has been done by Bell Lab from ROF to DITROF, renamed TROF with a version called NROF2 that is simply generating pages for teletypes. So since ROF is also an interpreter, making pages, making layout, using UTF-8 that is less than 8 bits, because not every sequence of 8 bits of octet is a valid UTF-8 value. Nothing can prevent from, for example, having a program called MS that will be simply a copy of Virtex, but using a set of macro written for TeX, doing exactly the same thing that the MS macro are doing for ROF. TeX is more general than ROF. There are very ad hoc things done with ROF, while TeX makes things a less restriction. So we can, in fact, replace ROF as a page creator by TeX, simply letting TeX mastering macros like the MS macros to produce the pages. So for me, the future of TeX and KTeX is in fact to do also what ROF is doing, and since ROF is not very easy to program, it is a bit awkward. TeX can be a bit awkward too. But for example, for manual pages, there is nothing that prevents using the TeX engine to do what rough is doing. This is simply converting the rough written macros, set of macros, in TeX understandable one. You can still write main pages using the syntax of the rough macro, and it will simply render the pages. I have some things to do still, quite something to do. To extend a little DVI, because the rough has added some primitive that are not in DVI, only 2. There is some peculiarities about the lines, because a rough takes beginning of a line to detect what is a macro and not a macro, so that this can be addressed. But in fact, what rough is doing can be done by TeX. There is nothing preventing this. So TeX can be the typography of a system. To go back to what I said about APE, we wrote it. I wanted Kekch to be exactly the same whatever the system. Because if you are asking a student to write something using TeX, as long as using TeX is exactly the same whatever the system, as long as they are using mainly TeX, in fact, to produce documents, you can swap the system. Meaning that as soon as they are accustomed to use TeX, you can replace whatever the system by Plan9, for example. They will not see any difference. The utility will be exactly the same. The commands are exactly the same. The produce is exactly the same. This is also for this that I use APE. There is a lot of details, and as you can hear, I read English without much problem. I can understand it correctly, but I speak it like a French. As you can hear, I'm not very comfortable facing an audience, so I will stop here for this point. This is the main things I wanted people to understand. There is an interpreter, but all the things that you see, name TeX, LaTeX, or whatever, or that could be MS, these are just masquerading for TeX. In fact, beneath all these names, there is only one engine. Since LaTeX has evolved, at the beginning, LaTeX depended only on TeX. Later, LaTeX asked to use extensions done by the NTS team with what is called Epsilon TeX. Epsilon TeX is an extension of the TeX engine. So I had to move to compile LaTeX, to move to the epsilon text engine that is TeX plus epsilon text. And now LaTeX requires even other extensions. So I had to write another extension, and that other extension is called prot. Prot, it is a French name, but in fact we stole it from the Italian. But it is a French name. Normally, the Marseillaise should. Prot is an extension of a TeX engine. In fact, it is an extension of TeX and epsilon TeX. So in Kekch, when I say there is only TeX, in fact, there is only Prot. Prot is compatible with TeX. We can switch to compatibility with epsilon TeX. So Prot can be used to TeX plus epsilon TeX. And it is also compatible with all the primitives required now by LaTeX. So it is compatible with Prot. So there is one engine, even if there are several distinct, apparently different utilities. There is only one engine beneath, and it is small, and it is only libc, nothing more. It's totally portable, and it is in fact what will replace eventually ROF2 in the future. That's all. I'm sorry for the speech. I'm sorry for the English. And I just wanted to spot this thing because TeX is, there is a lot of details to go into. So I just wanted to spot this thing so that you can understand a little bit to what I'm aiming now. Thank you.
Are you open for questions?
So for portability reasons and maintainability, have you looked at, and I have no idea whether it's what quality it is, but things like Protect that's written in Go, that's the essentially TeX interpreter written in Go. That's a new effort.
I want to stay with C because it is simpler. There is, for me, absolutely no reason to switch to another language. Knuth, as written in fact, is the main objective initially was this. It happens that ROF in fact was written before TeX was written. So we must make allowance to ROF. It is older. And Knuth benefited from lessons learned by ROF. Knuth, at one moment, was presented with a printing of his main work, The Art of Computer Programming, and he disliked it. Why? Because the technology has evolved, and the ancient technology was not available anymore. They have switched to digital, not digital typography, typography made by computer. and Knuf find the result unsatisfactory. He said, if my book has to be printed this way, I don't want it. So Knuf said, I will develop a program so that no one in the future can tell me I cannot make the book like you want it. This is why Knuf has developed not only TeX, but Metafont. Knuf had made on the layout engine, but a program to draw fonts. This is Metafont. And Knuf has also designed fonts, the computer modem. So he has made absolutely everything. And he has said, because I want in 100 years, even if all the printed version of my book have disappeared, that someone can reproduce my book exactly as I wanted it. For me, that's it. TeX is a complete solution, and Metafont is a rasterizer. Metafont, you define, in fact, lines, and it rasterizes the lines. It is a rasterizer. This means that in TeX, so in TeX, you have absolutely everything. For now, we rely on PostScript. There is GoScript. GoScript is a problem all by itself. It is huge. The version in Plan 9 is obsolete. It is a nightmare to update. And the license is a nightmare too. TeX is BSA licensed to MIT for prot, and it's not exactly public domain, but totally open for what the Knuf has done. So we have everything to compute the layout of the pages, everything to draw the pages, everything to obtain the image, the digital image, because Metafont is a rasterizer. So I can replace, in fact, everything. I can go to the specification, to the file text, to the image of the pages. This is the aim. GoScript will go to. Bye. Bye-bye. Metafont has been used to write Metapost, John Hobbies. Metapost is in fact a drawing program. Metafont was specialized in fonts. Metapost uses the same syntax, but to draw figures. The figures we have put in the paper about Nix, this is Metapost. This is made with Metapost. So Metapost can be generalized. Metapost emits PostScript commands, but it can be switched to emit DVI. I will simply extend DVI, and to rasterize DVI, I will extract the rasterizing capabilities of Metafont from Metafont. So I will have absolutely everything, totally independent from anything. So if in 100 years, I will probably not see the thing, if in 100 years someone wants to reproduce exactly the thing, it will be possible to reproduce it exactly using only TeX. This is the main point. So, Geoff, if I'm interested in Plan 9, this is for the very same reason as Geoff. I want things to be consistent, simple. I don't see why we have to complicate anything. We have everything here. We don't need rough and TeX. TeX is enough. We need only to take the set of macro used, for example, for manual pages. What is the problem? You use this set of macros, but TeX interprets. Why? I don't see why. So I'm hoping you see where I want to go.
So is there any way to generate plain text output from, like Rolf is currently doing? I mean, when you view a man page, your vision is that you're going to generate text to put into dev text, or you're going to actually have to rasterize the page with a
no.
Convert DVI and use DevDraw.
This will be done starting from DVI. In fact, I will there is DVI to PostScript from now, but I will make a DVI to whatever. So DVI will make the layout, but there will be a post processor, DVI to text, to extract the text for a TTY or for whatever. In fact, from DVI, all the outputs could be made. We can go right to the bottom to the image of the pages. We can stop at some level to extract just the text or not. Everything will be done from DVI.
Okay. Because I had thought of this idea too, like years ago, like why are people not using TeX more for just rendering graphical? Anytime you render text, you should maybe always use it, you know. But I don't really understand the DVI format very well, and so I just wonder, is the text actually in there, or is it actually just drawing primitives at that point? You're drawing lines.
In fact, the characters are there, but with a special encoding, because in DVI the encoding is a text encoding, but everything is possible from DVI. And I will extend DVI to cover what is possible with rough, but not at the moment possible with DVI. But everything would be done starting from DVI. One thing that could be done too, why not having a kind of utility called HTML. I have a set of macros, and I let TeX make the layout. So in a window, I feed HTML, and then I have the layout of my page according to the window. Why not?
Thanks for the deep dive. How far along are you in order for TeX to be able to parse MS macros?
Not very far. If I had the time, but I'm making too many things. I think I like everybody. I try to spare some time for Nix. I had to spare some time for Kekch to support user. I made an update for LaTeX some days ago. So LaTeX in Kekch is a very, very latest. So it's simply a matter of time. And if we can finally gather attention to Plan 9 and to this, I can have gladly some help. It's not difficult, it's just a matter of a bit of time. But I think if I could work every day on this, in a matter of 1 month, this is done.
I hope you find the time. Another aspect, DVI is more a fixed layout format, and Martin Ruckert has developed Hint, which is a reflowable text format. And the question is, it seems everything is now sort of pivotal around DVI. Are you thinking about also supporting Hint for a more maybe future-facing format?
This is the reverse. This is the reverse. Hint is using Prot. Martin is using my work. So this is the other way around. I made Prot as a change file exactly in the spirit of Knut and the NTS team, so that anybody can use it. And this is what is done by Martin Huisman with Hint. Okay.
So yeah, we got some questions from the internet. One is it fair to say that Truff is significantly simpler than TeX?
It is yes and no. In fact, in TeX there is no preprocessor. TeX is convoluted, is making a lot for the interpretation. It can be customized a lot, in fact. Truff is using preprocessor because the treatment of the macro is too limited in Truff. And Truff has also some ad hoc limitation inside itself, especially mixing things about fonts that are not to be done here. In fact, TeX is more general than Truff. So I can make Truff, there is a little work to do, but I can emulate Truff with TeX.
All right, and one last question. That's about the audience. Is Kekch meant for academia or rather personal use or commercial use?
Everything. It is not GPL. There is a commercial version using Kekch in fact, because the license allows this. But this can be used by absolutely anybody.
Right, then that concludes this talk. Thank you very much. I would be very happy. Oh, look. Hang on a second. To turn on the monitor. No, off. There we go. All right. So now the internet can hear me and you can, but without the echo. So welcome back from lunch. As usual, we're a bit behind in the schedule, but what do you do? And the schedule is messed up anyway. So yeah, next up we got Konstantin, and this is a remote session. So once again, we will be watching a recording, and then we will have a Q&A session over a Google Meet. And with that,
informatics at High. So, hi everyone, I'm Konstantin, and I'd like to talk a bit today about how Doom works on Plan 9. So, just a quick introductory note, I'm also known as Quix or Quix. I'm a PhD student in bioinformatics at Heinrich Heine University in Düsseldorf in Germany. And my topic is visualizing pangenomes, which is essentially very large graphs. But more to the topic, I'm also a long-time Ninefront user and contributor since around 2014. I've mostly done I've done some system work, mostly on the Intel graphics driver and like fixes and improvements here and there. But mostly I've been focused on applications, so games and audio stuff primarily. I got my start porting Quake 1 and 2 and Wolfenstein 3D, and I've worked on some original stuff. Also have an Pico implementation, which I've used for a whole bunch of stuff, and Pplay, which is like an audio editor similar to Audacity, but in a much more Plan 9-like style. So anyway, Doom. Doom is the ultimate time waster. It's one of my favorite games, and I've worked on a ton on it for Plan 9 and other platforms. But just to, for a quick recap, it was released for Microsoft DOS on IBM PC and compatibles in '93 in the US, requiring at least a 386. It was quite revolutionary at the time. It pushed the boundaries of 3D games, and its software was already kind of at the forefront of this with its previous games. And even though other studios were also making 3D games, they were definitely the ones pushing the boundaries with fast-paced 3D games. And essentially they defined the first-person shooter genre. They also popularized online play. I think they coined the term deathmatch, referring to free-for-all matches online. You also had co-op modes already back then. And they expressly allowed and encouraged modding through the file formats they used, and also licensing and other stuff. So you had tools like the Doom editing utilities on the left cropping up already, as the first public demos were appearing. And tools today basically descend all the way back to those made in the 90s on DOS. And in '97, the Linux port source code was published, which was fairly unusual at the time. It was fully in C, so unlike other previous titles like Wolfenstein 3D, which had a whole bunch of assembly in the source code release, and there's no floating point, it only does fixed point arithmetic. So as a result, it's very easy to port, and you have it running on all kinds of appliances and ridiculous platforms like PDF files or your bootloader, for instance. So just to situate kind of where Linux Doom fits in, on the left you can see the family tree of the main game releases, essentially, with Doom, Doom 2, Ultimate Doom, Final Doom, and Linux Doom over here. And on the right you can see that Linux Doom is essentially the ancestor or the basis for almost all of the source ports and also tools that are still active projects to this day, like Zendronim, for instance. And Plan 9 Doom is a direct descendant to Linux Doom. So Doom was initially ported by James Tomaszke, and I hope I'm pronouncing his name right, in 2009. Unfortunately, his blog posts and repositories are defunct, and I haven't been able to find any archives online, so I couldn't compare directly what he has done. But prior to Ninefront's contribution, existing input interfaces do not handle key-up events, so you only get pre-composed runes, for instance, whenever you type a key. And this is a problem for Doom and other games where certain actions like firing or moving is active until you release the key. So something different was needed. Shortly after Ninefront's inception, KBDFS was released, and it's essentially, to oversimplify to the extreme, it's a file server which provides this new file defkbd, which translates raw keyboard scan codes and provides kind of these events identified by a character. So it's either like a pre-composed like a rune here, or a key down or key up event, and every event gives you the entire set of keys pressed that are still pressed at the time. So there's no possibility of stuck keys, for instance. And this is very nice for emulators and for games like Doom, for instance. So I'm really simplifying this. But anyway, Doom was imported into Ninefront shortly thereafter, already using KBDFS. And ever since, it has seen a lot of fixes and changes. So a lot of bugs were fixed, typical to DOS game ports, like assumptions about pointer size or pointer to integer conversions, evaluation order bugs as well, and other undefined behavior. We have fixed a bunch of cosmetic engine bugs. So, for instance, sound effects being played twice or not at all, or stuff like this. Things that were known from different versions of the game. We've added compatibility switches for demo playback. So demos are these demo loops which record player input and then just play it back, kind of like on game consoles like the NES, where you have a demo loop at the beginning before you press any keys. And a lot of people still today record and play back demos for speedrunning or for competitive multiplayer stuff. So it's nice to have these working. So we've also raised some of the static limits. So for instance, number of objects that are visible at any time. Maps being made today are much, much bigger. And we've made some performance improvements, which I'll mention later on. So the first compatibility switch is for a bug in Doom 2, which was later fixed in Final Doom. Lost Souls, so these flaming skulls there, they launch themselves at you, and they were supposed to bounce off of you and of walls, but there's a typo in the code that just skipped all of this, and as a result, demos recorded with the Doom 2 engine will desynchronize. So the compatibility switch just disables this this behavior to allow correct playback. And the second one is about another bug, this time in Final Doom, where teleporters don't reset the player's height, essentially. Allegedly TMT and T, so Final Doom is TNT and Plutonia. Allegedly they commented out one line of code here with a comment, is this even useful? Apparently it is. So this switch just disables this this line of code. Okay, now moving on to game data. Every version of the game has its own set of files, but the way it was supposed to work back then is you have every game installed in its own directory on DOS, and you CD into it, and all the save games and screenshots and so on are stored there. But for Plan 9, this is not exactly what we want. Preferably, we would have the game installed like system-wide, and then each user would have their own directory with files per version. And usually newer source ports add a whole bunch of code to implement more configuration file options and to manage user and system directories. But instead of this, we can just use namespacing. So with a fairly simple script, we can just use like a global mount point, for instance, in the user directory in libdoom. Then we can bind game directory, user game directory on top of that with the create flag. Then on top of that, also bind the system files for the given game. By version, I mean, Doom 2 or Ultimate Doom or so on. And then we just CD into this. And as a result, every file, such as, every new file that will be created will be stored in the user directory for that specific version. So everything is nicely segregated, kind of just like this. And this idea has been implemented and shipped in the Ninefront distribution's launcher script. And this is kind of what the file organization would be like. So in the user directory, you'd have a config file, which was global, but doesn't necessarily need to be if you create it in one of these directories. But anyway, and here we have files for Doom 2, Plutonia, and Ultimate Doom. And as you can see, the screenshots here in PCX format and the save games all have they don't identify the game version just with the file name. So this is why we put them in separate directories. And then the system directories can also contain stuff like mods, which are usually fairly large files. So, better, I think, to avoid a bunch of duplication and have everything at one place. So what are these game files? They're called WAD files, short for where's all the data. And you can think of them as tar files, essentially. They're an uncompressed collection of concatenated files, also referred to as lumps. And they're organized into sections, also referred to as namespaces, via these empty marker lumps. So I've marked a bunch of them here. They're just zero-length, like virtual files, essentially. And then in-game lumps are looked up back to front, meaning from the end of the list of WAD files all the way to the beginning. And some of these sections are cached. So instead of looking up the start of all P lumps, for instance, the location of these P end and P start are saved. So what kind of files do we have in WADs? Well, we have music files or lumps, in MUS or MIDI format. And MUS is a subset of MIDI. Digital sound effects stored in DMX format. We have graphics as texture patches. The textures are made up of one or more patches, just squares. Flats are textures used on ceilings and floors, and sprites is for player graphics, objects, and so on. Weapon graphics and stuff like this. You have level data, so all the lumps for every map. You have demos, color palettes, and screens, and special stuff like this. But this is basically the the kind of file formats you have in there. The way these are viewed and edited since the DOS days is usually with these fairly large and graphical programs that are aimed to be more or less all-in-one for convenience. So they have to handle, opening, creating, writing WAD files, and they also handle different, they can, for instance, play back music or sound effects, or have some, primitive map viewing or editing mode, or preview of file types, basically. And WADGadget, which is created by Simon Howard, the author of, or one of the main authors of Chocolate Doom, I think, is a tool that came out very recently and is for the terminal. It kind of follows the same trend, essentially. Well, what could we do on Plan 9? Well, recall the tar file analogy. This all maps pretty nicely to just the file tree. Like the marker lumps basically delimit the start or end of a directory. And so it's very easy to, the correspondence is pretty much direct. The only caveat is that we have to also store these end markers as these synthetic files, and I'll explain why a bit later, but that's it. And once you have this, nothing else on the system, no other tool or editor has to care about the format of WAD files anymore. So yeah, the end marker hack is necessary because, as I'll show a bit later, we have to be able to rename these to kind of override the start and the end of a section, and this is necessary for mods. So these need to be modifiable. But going back to the list of file formats, we now have basically handlers for every single one of these formats. So we have a MUS to MIDI converter, we have more than one MIDI players, we have DMX deck for the digital sound effects, we have decoder and encoder for the different types of graphics, and there's a work in progress map viewer / editor, and random scripts for like color palettes and stuff like this. And so yeah, just to illustrate the overriding the end markers, here in the main WAD, so for instance for Doom 2, you have the S section going from S start to S end, and if you want to override one of these lumps, such as this one, which is the first frame of the punch, you have to override the end of the section. So since lookups start from the end, now once all the WADs are loaded, lookups will start from here instead of here, and we'll be able to override this lump. And that's basically how mods work. Now the limitations in the vanilla engine, and this bit me just a couple days ago, is that this isn't implemented fully. So actually for flats, so the F section, it works fine. For sprites, duplicates are disallowed, so this actually does not work. You have to either modify the main WAD or just copy the entire S section and like override it that way. and for texture patches, it's completely ignored. So newer source ports fix this, and I think I'll also fix this in a short order for our port. But this is the limitations for vanilla. So as an example, and I mean I won't go through the whole process, but here's how, for instance, we can change the sky texture. So taking some picture, we just have to resize it, crop it, rotate it. We have to, change it to CMap 8 format. Then we create a new WAD file, encode it as a Doom graphic, and put it into this WAD file, and then we can just load it, basically. No, wrong map. I think this one works. And there you go. Now you have Total Blender as the sky texture here. All right. And just as another small example, we can also change like weapon sprites with like what I tried to show in the different listing. And here I just changed the first frame of the punch to cat clock, so you can cat punch people. So this is, it's pretty simple to do. It's very scriptable and so on. So the WADFS approach is very powerful on Plan 9. But it's also because we have full control over, all the utilities, and everything uses the same interface and so on. So moving on to maps. Maps are this collection of lumps that describe the geometry and the objects in the map, and there's also separately almost a bunch of lumps created by like a pre-processing step to pre-compute this binary space partitioning tree. And this is used for line of sight, for visibility, and a bunch of other stuff. I won't go into detail into this, but technically it's a separate step, and these are somewhat optional. But all I want to say here is that basically these correspond to two separate tools. Although usually modern map editors integrate this, the node building. When you export the map, you also build the node map. So right now, it's not included in Ninefront, but there is a primitive kind of map viewer called dmap. And it just, visualizes different parts of the map. There are 7 different modes. I can't even remember how to switch between them, of course. Well, it doesn't matter. But I mean, you can visualize different parts of the map, properties of the different objects, but you cannot yet move anything around. Or modify the actual map. Still work in progress. I wouldn't do a node builder from scratch just because over the years, and it's been 30 years now, a lot of the node builders that have been made have had various bugs and limitations. So this is not as simple as it looks. But there is a project I found from a couple of years ago that might be easy to port. And as an alternative, we could just skip this whole part because it is an optimization. But whether we skip it or not, we have to write a bunch of code. So it's which approach to take is a bit debatable. So moving on to music. So the way sound works is there is a bunch of digital sound channels which each play one sound, and one music channel which where something synthesizes music from one of the MUZ or MIDI files. And these are more or less independent. The DOS version originally used this DMX sound library, which both John Carmack and John Romero have expressed regrets about. But in any case, the consequence is that there is no sound music playback code in the source code release. So how could we implement this? Well, we may as well just reuse the MIDI players and most to MIDI converters and stuff and just fork an exec and RC script. And this is, in essence, all of the code that's necessary to do this. You just create a pipe, and then all this file descriptor dance here is to hook up the standard output of the script back to like this pipe. So on every frame, we just read a bunch of music samples from the pipe and mix it in with a bunch of sound effect samples and output this. So it's pretty simple. And just to illustrate one of the nice side effects, which is, so it's both simple, but it's also very easy to switch to a different music synthesis engine. So the very first one, I will showcase just a couple of them, but the very first one is Games MIDI, which is the first MIDI player that we had on Ninefront, very old one. It just does sine waves basically for every channel and mixes them together. So it's pretty primitive. It works, but you might want something that sounds a bit better. So here's a MIDI player with OPL3 chip synthesis. So since you're launching the script every time you change a track, all you need to do to interrupt is to close the pipe. So you can change stuff on the fly. So here's using a sound font. Oof, okay. Maybe let's demo the iconic E1M1 music. So this is with OPL3. Sound font. So this is with SC55 sound font. And finally, well, okay, there's two things I'd like to showcase also. One is using a USB MIDI synthesizer. So here it's one that does Roland MT32 emulation. Just need to, does it work? Hopefully it works. Let's see. So essentially, instead of launching a player, it passes the MIDI instructions through USB to this USB sampler, which to this USB sound synthesizer, which then writes samples to a different output. I have a mixer hooked up, so this isn't receiving any samples back. So this is why I need the dev0 here. Let's see, hopefully it works. So it sounds pretty good, and you can select the sound fonts and everything, so that's nice. It does use sound font for the emulation. It's basically a Raspberry Pi. Anyway, I think you get the point. And lastly, this does receive the name of the lump you're trying to play. So you can basically just play MP3 or Opus or whatever files instead. So instead of doing any kind of like music synthesis, you can just play MP3 files. All of this works, and it doesn't require any extra code. So this is the synthesizer. I was using the Serdeco TM32. Okay, so just some notes on the networking model. It's a peer-to-peer architecture where 2 to 4 players launch like independent sessions of instances of Doom. Either through IPX or Serial. The connections were externally managed, so it just set up a bunch of stuff and then launched the actual game. On Linux we use UDP/IP. So the simplest way to get any networking going is just to port the UDP/IP bits, which is, there really isn't that much to do. You just need to announce an open port and then connect to 4 other players. You can even use a CS to look up like host names and stuff. In the source code there is a comment about using 9p, but I'm not sure if that... we can discuss this if you have any ideas about this, but I thought UDP/IP would work in general better, also for performance. So here's a photo of a one-man LAN party I set up a couple of years ago, and I just linked up a bunch of computers, including this Pentium 3 over here, and unfortunately, while everything worked, the frame rate was really poor. And the problem is that on every frame, every player has to synchronize with every other player. So send the tick data and receive every other player's tick data. Tick being like the frame update, basically. And if they're not received in sequence, they have to be retransmitted. And there is some buffering, but very, very fast. If one of the machines, like the Pentium 3, is slow, then the game is very slow for everyone. So, especially for playing over the internet, we'll need to make a different protocol in the future. And finally, some notes on performance. So Doom runs at 35 frames per second. It has to read input, update the game simulation, the game world. It has to render a frame. It has to do color palette conversion and integer scaling from 320 by 200 pixel internal frame buffer to, like Full HD or 4K or whatever sized window. It has to also mix sound effects and music and do sample rate conversion to the dev audio format. And it has to do like receive and sending and receiving stuff on the network. the biggest bottleneck here is drawing to the screen, doing the scaling, followed by the palette conversion, and then the reading in and mixing music samples. So for scaling, and I'm not sure who came up with this idea initially, but essentially we can just in the code scale pixels horizontally, and then we can use the replication flag in a lock image to scale vertically. So we draw one scan line at a time over a rect that is as big as the scale. So for instance, 4 scan lines for 4 times scale, and then draw just reuses this one scan line and replicates it like 4 times. And this is way faster than just doing this manually and uploading a huge image. Then to avoid stalling, we also much later added like a synchronous drawing with multiple buffers that are being flipped continually. And for ARM64, Sigrid also contributed the assembly version of the palette conversion stuff. So this made it quite faster on the Mount Reform laptop, for instance. And finally, for sound, the problem here is that we're forking an RC script, and this RC script can be doing anything. So to avoid any kind of stalling anytime we start it or try to read in music samples, this has been put in its own process. So there is a bunch of stuff still that needs to be done. Loading lumps and wads from paths is kind of annoying still. Specifying the full path doesn't really work. There are some limits. For mouse grabbing, it might be nicer to enable some delta mode in the kernel driver instead of warping the mouse anytime it moves beyond like a rectangle in the center of the screen, which is basically how it works right now. Might be nice to add features from Boom and other source ports to be able to load newer maps as well, but this quickly gets pretty complicated because a lot of these features are quite bonkers. So we would need better networking code. Sorry. And we would like some level generators as well in future. So we might port Chocolate Doom and maybe other source ports as well. But thanks to Sigrid and Moody's work on Nope, we have a bunch of game ports of Heretic, Hex, and Duke 3D and stuff like this. And we've come to realize that a lot of the code that we have to add for drawing to the screen or doing sound and so on, it's kind of mostly the same across all of these ports. And the emulators, the console emulators in Ninefront already unify a bunch of this code into this file EUI. So we could do later probably a library or just whatever that provides some kind of framework for these ports and just does all of this, just provides all this functionality already. So in conclusion, we are Doom ready. We have a fully functional Doom port. It works on all architectures Ninefront has been tested on and has graphics for. Most of the utilities I've shown are included in Ninefront, except DMAP and also the sound font MIDI player. But yeah, and there is some work to be done, but in the end, we're just fooling around. And yeah, here's the names of 2 books that you might want to look into. The first one is The Story of Id Software, and up to about 10 years ago, I think. And then the second one essentially is a 400-something page book that details every single aspect of the Doom engine. And the same guy, Fabien, has a book for Wolfenstein 3D as well, and I think some arcade systems. Very cool. And there is a YouTube video that has been recorded in id Software's offices right before the release of Doom. So it's an interesting look at its development. And yeah, that's it for me. Thank you very much.
All right, so to everyone watching us online, we're doing the Q&A now, and just waiting for Konstantin. We couldn't prepare the Google Meet beforehand because otherwise the laptop was a bit overwhelmed. I'm checking if we already got any questions here. Oh yeah, we actually do. All right. Sorry?
It should be in his email, right?
Yeah, I just sent him. Yeah. Oh, there we go. Yeah, sorry. Stupid stuff. Admin. Alright. So you should be able to hear us now. Hello. Excellent.
Hey.
Yeah.
Can you hear me?
Yeah, we can hear you as well. So, we do have a handful of questions. Does anyone here in the room have any, actually? No one? I think everyone was just overwhelmed because it was so awesome.
Yes. Thank you.
All right, first question is coming up.
This is more of a share than a question. The portability of Doom, and you had it in PDF Doom. Have you seen the TypeScript type system version of Doom that it produces one frame every 12 days?
Oh yeah, that was one. That one was insane. Yeah.
Hey Daniel, awesome work, by the way. Thanks for the demo, and yeah, very inspiring. My question is about the internal frame buffer and how you move the data into DevDraw. Did you Did you consider maybe revising or reviewing the engine itself to use the DevDraw instructions to render those pixels right in the DevDraw buffer? Because essentially what you end up here, you render it in frame buffer, then you copy those pixels into the 9p message buffer, and then once again in the kernel to the screen area, right? So you have triple copying. Or as an alternative to speed it up, maybe, well, of course it will break draw term, but you can seg attach the frame buffer from the screen and render directly there. So any considerations in that area?
I'm not super familiar with the architecture of DevDraw, and I haven't deep dived into this yet. I don't know, it might be worth a try, but I don't know how much of an improvement this could actually make. I know that for Quake, Sigrid has she has an experimental branch on the Quake repo where she basically directly renders, so without any color palette like conversion, so it skips this entire step and just does RGB24 colors directly. But I'm not sure. I'm not sure how you would do this fast and well, like for scaling, for instance. If you have, like for 320 by 2200 pixels, you know, there isn't that much data to move around. But once you have like a 4K window or something, I mean, yeah, I'm not entirely sure. So I can't give you a very intelligent answer about this. But yeah, might be worth a try. I don't know.
All right, and I'm reading the question from the chat now. How bad would it be to leave the audio mixing to MixFS instead of doing it internally?
So I think we've played around with this at one point. The one reason why I did not personally want to go this way, but then MixFS, there was a bunch of changes to MixFS afterwards. But one reason is to have working volume sliders. So for music and for sound, you have separate ones inside Doom, and it is useful to have them working. So there's small problems like this, but I don't, in principle, I don't think it would be like a huge issue or anything.
All right. Looks like that's it. Nobody else is moving here. So yeah, thank you very much again. And we will make sure that you also get a tiny 3D printed Glenda to you. Thank you.
Awesome, and thank you. Thanks to everyone. Thanks to Anthony also, and for your patience and rescheduling and swapping all the talks and all this. Have fun.
Thank you.
1, 2, 3, 1, 2, 3.
Okay. Sounds good. Sounds a bit French.
We can fix that in post.
All right. Yeah, stage is yours.
I thank the Plan 9 Foundation for the opportunity to talk about one of my goofier projects called Amber. And Amber came to be through my studies of the Plan 9 literature, where I somewhat inevitably came across Mr. Rob Pike's paper describing the Windows system 8.5 in 91. And as a short reminder, 8.5 is the predecessor to Rio, which is the predecessor to Nile, which Mr. Anthony Soros talked about yesterday. And I will bring up the family tree Amber sees itself in again later. When I read the 8.5 paper for the first time in April of last year, a deep feeling of awe came over me. And in my then established context, not knowing of Plan 9, only the heavily weighing behemoths Xorg, SDL, Wayland, and maybe Quartz and DirectX and Ncurses made up my understanding of what computer graphics windows are. I felt as a lone archaeologist uncovering the remnants of a lost civilization still faintly gleaming of long-lost power. And it is this fascination with the 34-year-old technology I hope to in parts share in the following quarter of an hour. Alas, 8.5 is wholly inaccessible. 8.5's bedrock is Plan 9's kernel feature of constructing per-process file system views with /def/bitblit and the other devices' meanings varying based on who writes or reads from them. I know of no other way than intrusive kernel modifications to recreate this environment on modern Unix. Not even Fuse, which can emulate some of the custom file servers present in Plan 9, to my knowledge, tells the virtual file who opened it. And to fully switch to Plan 9 for my daily driver is not an option, as I don't own a 3-button mouse. Yet it turns out that 8.5's use of the file system namespace as a communication primitive isn't integral to its concurrency and self-similarities. As both of these properties were already present 2 years prior, implemented without the Plan 9 kernel. And it is this very paper, A Concurrent Windows System, Amber is an artistic study of. Before going into detail about window managing, I want to talk about one promise communicating sequential processes holds for the human-machine interaction setting. CSP is all about various agents, the sequential processes trotting along at their own pace sequentially, and then at points they understand communicating with one another before falling back to their sequential routine. As explored in 85 in the Squeak, a language for communicating with mice paper, statically unrolling the combinatorial explosion generated from these interactions is a non-trivial compilation step for Squeak. And when this unrolling is done manually, as is the case when writing for a traditional event stream-based system, failure to precisely cover the semantics of each case leads to buggy behavior. The promise, then, is that by using a runtime scheduler to implement CSP, the combinatorial explosion is contained and encoded into the dynamic state space of the running executable with precise semantics lexically defined in the CSP language being followed to a T. And while I struggle with the myriad of hiccups present graphical user interfaces present themselves with to me. Most infuriating to me personally on a daily basis are the inconsistencies, graphical bugs, and periods of unresponsiveness on my TTY as exhibited by the editor Vim. I won't berate Vim any longer, as after the passing of Bram Molinar, I'm much more inclined to praise Vim for being one of the very few keeping the VI way of thought alive for over 30 years. Having now connected the CSP promise with the TTY, I can finally state what Amber is about. Such Amber is an implementation of a concurrent self-similar Windows system inspired by the ideas presently discussed, driving the TTY as flavored by Xterm. To summarize, I have put together an excerpt of Amber's family tree spanning over 40 years from the original CSP paper in '78 to 2024. This arrow from CSP to Plan 9's rendezvous system call is an artistic liberty of mine, but I put it there to emphasize the secret sauce in 8.5 as the semantics of read and write system calls blocking are synchronization primitives analogous to CSP channel operations. And precision in concurrency semantics is vital for the system. Even a little slag is seen in some network file systems. Showing such slag isn't a deal breaker for traditional file systems, undermines the design of the entire Windows system. Along the top line, you can see the evolution of how CSP went through the various languages to land in a concurrent Windows system. And this eventually led to 8.5. 8.5 then gave Rio, which then inspired Nile. But the CSP lineage went further through the decades, through the various languages, and then with other influences fused in 2009 into Go, and I wrote Amber in Go. So the '89 paper, Concurrent Windows System, together with Go, then gave rise to Amber in 2024. So what makes up a concurrent Windows system? This is from the original paper. You have a client, and this client knows about itself and has a precisely defined interface with the world. In this case, some graphical window capability and then keyboard and mouse input. For Amber, this interface looks like this. So I have a capability to get the dimensions I need to draw myself in. I have a capability to push a char map out, and I have a capability to get keystrokes in. And then there's also a suspend capability, or there's also a terminate capability, and crucially on the TTY you can press Ctrl-Z, so you have a suspend capability. There are certain special properties of the TTY as compared with traditional GUI environments. And these, for one, are that the entropy in each frame is small enough that you can actually shove it fully through a channel. And because the TTY is based on standard file descriptors, there is no master clock for some FPS. There's no master clock, so you can leave the entire concurrency of the system fully to the scheduler and get updates events as they come. And one property I like in particular is the modeling of the suspension capability, in which I used a triple channel, which only is possible in languages which have non-statically named channels, such as Go. And this was something which, in my understanding of the language family, became possible in the limbo area, in the limbo times, where you have some global garbage collector which takes care of these channels. And so maybe at first glance the channels all point in the same direction, but the owner of the channel changes. So a client is notified it should sleep, and then it can notify back it's ready to sleep. Then the master TTY driver can actually put the OS to sleep, and when it gets the wake up signal, it can then relay the waking up through the chain. And so this makes Control-C a self-similar operation. So Control-C can fully propagate through the system. Okay, I have a demo. So you can see that it works. So in this demo, I have one coin process which spins a coin, and then I have a window manager which puts two windows side by side. And so you can see at the bottom, at the very bottom, this is selected. So I can select from both of these windows, and then if I am inside this window, I can select these two. And so I can change the coin's height, or I can reset them, or I can reset their angle, and it propagates fully through the system, and also resize events are fully propagated through the system. And if I put the executable to sleep, it truly sleeps in the OS sense, and then I can wake it up, and it propagates the wake-up call through the managing windows and through to the individual. And I can also quit. And if I quickly look at the implementation, it is really it is really a very simple core, in the sense that you drive with a terminate capability, because the Control-C key gets pushed through as a key. And so if I want to use it, I need some sense of looping termination signal. But then I manage a coin process and a managed double coin process. And these coins also turn at speeds which in seconds are reciprocal primes. And so if you had a system with a master clock, to get precisely these concurrency semantics, you would need an enormous frame rate. But because the scheduler knows of a much finer, or has a much finer time control, you can describe these very concurrently intricate systems. And as a closing thought, one thing I want to add is to use pseudo terminals to get the other side. So I'm currently driving the TTY, but it would be nice to have the other side so that I can define a network protocol for the channel interface, and then emulate SSH's pseudo-terminal, and then some coloring possibly. And my ultimate goal is to create an editor I like. So I want to recreate Vim, but in a somewhat more concurrent way. And so Amber will be the basis of that. Thank you.
Awesome stuff. We're not seeing any questions online. Anyone here got any questions? Please queue up at the mic.
Are you aware of charm.sh? It's a Go library to do stuff with the terminal as well. They do have like some kind of transparency as well. Not as well done as
Jam.sh?
Charm, CHARM.
Charm.
Yeah.
Charm.sh. No.
Yeah, it's a Go library for like colors and all sorts of effects and charm.sh is the website. All right, looks like that's it. Then thank you again very much.
So I'm going to talk about static initialization of Bitfields in the Plan 9C compilers, and the rationale for this, it's a patch for the compiler, is that the Plan 9C compilers, they don't fully support Bitfields. They do support it somewhat, but in some software, POSIX software, not in the Plan 9 code base, there are other use of Bitfields that in static initialization of Bitfields instructs that does not work in the Plan 9 compilers. And this is one of the things that is in the NetSurf web browser that we had to patch manually to get by this. It's not a big thing, but it's one of the things, and I tried to solve that one, and also in other software like GNU-Make, and some other software also use this kind of initialization of Bitfields. So this patch makes it easier to port this kind of software. So Bitfields, for those who are not familiar, is a way of packing more compactly data into a struct to use every bit for something without having to use bitwise and or bit shifting. That's an alternative. So you use integer types, and you can specify how many bits each member of the struct is going to have, and then you can access these members almost like if they were a new kind of data type with a specified length. You cannot take a pointer of them, and you cannot do everything, but you can do like that. And outside of Plan 9, the C language have had Bitfields since the start. I tried to pinpoint if it was not exactly from the start, but I mean, what I understand, it's from the start. But it's not very used generally. Of course, space to compact space is less important than speed, and using Bitfields means that internally it's going to do some bit shifting, which makes it slower than just to take a full integer, for example, the machine word. And another problem that limits the usefulness is that the layout, exactly how it is compiler dependent. So the standard C standard doesn't specify exactly how these Bitfields are going to lay it out, and that means that they are less useful for specifying protocols like network protocols or interfacing with hardware by bit. And in Plan 9, so it's supported to do runtime initialization. You have Bitfields, and you can assign them values. So it means that this will generate code which shifts in the right values into the thing. But you cannot just take a struct here, bf2, and assign it a constant array of values that gets into the right bit fields of a struct. That does not work. And generally, it's not bit fields are not at all used in the Plan 9 core, but it's used in, for example, Ghost script and audio players. That's in the things that are shipped with the system. I was looking in Ninefront. I think it's similar for generally. And the probable lack of the support. Why didn't Ken Thompson, or who was writing the compiler, implement this? And it's of course it's not needed. Maybe in the Plan 9, so and it's maybe not so much used. But a probable reason is also that it's kind of a little bit tricky, because when you have an array. Normally in Plan 9, these constants, every member of the structure generates one data line or multiple data lines if the constant is more than 32 bits. But it's not like one data line is for two members at the same time, which is a requirement for Bitfields, because the whole idea of a Bitfield is that you can map multiple values into one 32-bit constant. So to do that in the compiler require either back patching or look ahead. So to construct these constants. So that is my assumption. That is why they left it out, to make it simpler. So I made an implementation which uses back patching these 32-bit constants in the output tree of the compiler. So if you have a struct, and and here are some different members, and here comes the first bit field, and then comes 6 bit field, and then comes something else. So when it comes to the first bit field, it generates a 32-bit constant, and the right bits are set into that constant for that one, and the other are left 0. And then if it comes another bit field, that would fit in the first constant. The first one is back patched, the first constant, and until it comes to a overflowing, like there is the next one, I should go into the next constant, so a new constant is generated, but like that. And this back patching is simply done by keeping a pointer to the last 32-bit constant in the output tree, and then so then the data lines are generated and sent to the assembler after. So it's from this data tree automatically. No change there needed. And the pros and cons of this current implementation is that the advantage of this patch is that it's what I can see is the minimal patch. It's like it changes as few lines of the compiler as possible to make this. But it has a drawback that it requires a separate modification that is similar, but in every architecture, it has to be made the change for them to work. It's not possible to just do it in one place, but it has to be done in multiple places. So I made it for those architectures that I currently can run on Ninefront. So it's ARM64, ARM64 and 386. It's made on that one, those. But if a new architecture is added, it has to be added there too. So it's and I mean, usually you just want to make a change in one place if possible. And all these architectures happens to be little endian, which means that the patch is even smaller because for a reason I will just come into. And the thing is that this pointer is a pointer to a long to this 32-bit word. So, but in the 64-bit architectures, this the member, the variable that keeps this 32-bit constant is a 64-bit memory position. So even if it can never be more than 32-bit because the constants are only up to 32 bits. So it works for anyway because it just writes to the lower 32 bits. So in this way I can keep. I just have to change. Yeah. In the other part, like SVT, this is for every architecture, and the DCL, the one that is the receiving part, it's the same. It keeps the same as no changes. So, but it's if to make it for big endian, so it have to write a little bit more code, but still. So the patch, this is just the patch description. It's on my GitHub page. And also, it's included in Ape XP. It's an experimental new Ape environment that is Jens Ståhl is making, and he has included this patch into this ape, which also includes the compiler. And his aim is to make ape that can environment that can compile more kind of software into Plan 9, and also to experiment with these kind of things without having to things have to go into the to the main compiler. Maybe it's not wanted to be there because it's just for porting software. So that's where it lives. So discussion is this kind of thing would it at all be interested to have support for this kind of thing in the mainstream compilers? It's a little bit I mean, it's not used in the Plan 9 system, but it's used for compiling POSIX software. So and it's part of the C standard. So, but many things are part of the C standard that is not supported. So it's not. And also, I'm a little bit curious. If there is maybe someone has an idea of how it can be made architecture independent, because I didn't figure that out myself. If there is a nicer way of doing that. So that are my discussion questions. So maybe you have other questions. Anyone? Yeah, they don't like Bitfields like that.
Lots of reasons for that, but it was a slightly later addition to C rather than being there from the start. It was added for as I remember it was added for a particular project. A particular group wanted it, and that's why it has so many bad edges. Really, if you were doing it now, you would at least have the ordering consistent somehow, so that you don't have. So you could describe protocols with it.
Yeah, that makes sense.
In some ways, that would probably be the most common application of it if it worked. And instead, you have if-defs, bracketing, each stuff that goes each direction. So but yeah, so it's useful to get it fixed in a way, because it's slightly annoying for it to be there, but not actually work very well.
For the presentation, very interesting, and actually made me think this how to make it architecture independent. The problem, like I'm thinking, looks like just pushing bits down to a shift register. So maybe like something abstract, making like push this many bits into the register, maybe using the architecture independent equivalents, just common shift and end and or operations. Make it a VLONG, probably let the compiler handle it, and that maybe actually simplify it. And thanks for the net surface, by the way.
Basically just echoing, I don't see any reason why we wouldn't want to commit it to the compiler, given that it's not a big change. And I think I'm not familiar enough with the code off the top of my head to say that we can make it architecture independent, but I wouldn't be surprised. There's a lot of stuff. It might be a bigger change because the compilers tend to have a lot of stuff that's copied and pasted, where we could refactor it to be. There's a lot of the architecture-specific parts of the compiler that shouldn't be architecture-specific. We should fix that. I think that's the short summary. And the way I would do this is first just commit this as architecture-dependent and then start refactoring.
I'm going to be a terrible man and take the opposite position. And you know, historically, the reason that Bitfields were hated is because people would pack registers that way for hardware access, and this caused endian stuff to get encoded into whatever applications you had. And now you're in the world of if-defs and figuring out what you're doing with your endianness, and it gets crammed through the bit fields. So they wind up being, hardware or endian dependent and architecture dependent in horrible ways. And so part of me, being contrarian, would say, why don't we just get rid of bit fields? And that way this compiler could be simpler. And anyways, they are useful, but there's a reason that we don't pack them generally. So anyways, there we go.
Okay, so my other idea is that I've read the patch, and the thing is that the architecture independent code calls a function gextern, which is architecture dependent, and once it's called, it's done. The data line has been emitted, written, whatever, but we can defer calling this gextern until we know what exact value is the composed from all the bit fields that compact into this single memory location. So we can act not call gextern on the first one and then retroactively patch the thing that is inside this structure that is already printed or something. But we can first construct it so that the value is correct, and then once it's done, so the moment we encounter a non-bit field or the structure closes, we can emit the bit field that is pending.
Okay, yeah, it's a good idea, yeah.
Is the C standard requiring the packing of the bit fields?
It does, yes.
It does require?
It does require packing, yeah.
In this case, for the big endian and 64 bits, since you will emit only when you have completed the pack, can you simply temporarily consider the packing like little endian, and once you have everything, swap the definition of the bit fields to be in a big endian order?
I mean, the constant is always 32-bit maximum. In Plan 9 compiler, you cannot have a bit field that is more than 31-bit or something like that. It's maximum. So I think generally the endian is not a problem. It's not to be used for communication, like where with different systems, I think. But that's and actually the format is specified. Like if you have a struct with bitfields in the compiler, it's done. Like it's not like it's not defined. So when I calculate this, I just have to calculate it in a way that is compatible with the runtime, because in runtime you can set these values and it will know where it is and this how it packs it. It's well defined in this compiler in Plan 9. So even if it's not set in the standard, so I suppose it's possible to do in different ways, because the C standard doesn't say, but the compiler do in one way.
On all Plan 9 compilers, long is 32 bits.
It's the bit field. You cannot have a longer than 32-bit, 31-bit bit field.
The long value is 32 bits in every compiler, including 64 bits.
Yeah, it is, but they use VLong and that 64 bits to hold the value in the
okay.
I mean, it's a general register that can be used for different things. So it's not. It just happened in this case that it's used for Bitfields, but it can be like it's called vconst. So it's something like that.
Right, and we got another last remark from the chat. Someone hasn't heard of Bitfields in C before, and they're saying it looks a bit like, or feels like a mix between structs and unions. Do what you want with that remark.
Yeah. I think you can have Bitfields in unions too. So
I can only say from my side, I do lots of firmware stuff, and I deal a lot with registers, which have very fancy bits in there for all sorts of stuff, and it's very handy sometimes to have Bitfields. Anyway, that's it, I suppose. Then thank you very much.
Thank you.
here. All right. So next up now we have Moody, and he will be talking about Unicode. And yeah, if you would please start your screen share. It just worked before.
Yeah, I'm sharing right now. I'll share again.
All right, I'm not seeing it. Let's see what happened there. Oh, yeah, there we go. All right.
Coming through all right?
Yep. And then let's start.
Welcome. So my name is Jacob Moody, and we're here today to talk all about Unicode. So just a quick brief about me. I work on Ninefront. I work on all sorts of stuff in Ninefront. I consider myself kind of a growing Unicode nerd. I didn't know much about Unicode before starting work on Plan 9, but have been growing that muscle. And I port stuff sometimes. It's kind of the bulk of the need to know. So I want to start with some historical context. And, this isn't exactly my story to tell, but I think it provides some good context. This happened years before I was born. But Unicode v1 was released in 91. Sometime thereafter, Plan 9 starts to kind of add support for this brave new 16-bit character world. And the initial port, at least according to Rob Pike, used an encoding from ISO 10646. And again, according to Rob, this was not very well enjoyed by those working on the system at the labs. At some point, Ken and Rob were asked to kind of vet a file system safe UTF design by some folks involved in the X-Open standards organization. In response, Ken designs what would become UTF-8 in response. Rob works on implementing support throughout the system, and under a week later, they ship out a build of Plan 9 with everything included that has this kind of UTF-8 support. And supposedly this was used as a argument for standardizing this encoding. So, Plan 9, stopped being developed by Bell Labs and kind of got out into the community. And of course, Unicode continued to change over that time period well after Plan 9 had kind of stopped being developed at Bell Labs. Perhaps the biggest change to Unicode, and probably the biggest change throughout all of its history, was Unicode extended to 21-bit characters and V2 onwards. They initially tried to fit everything into 16 bits. It's a bit ambitious. But they ended up giving up on that, and we now live in this 20-bit character world. I believe, from what I could gather, 9atom was the first to implement support for 21-bit code points. And, likewise, we have some library functions which work using kind of the existing properties of Unicode characters, and we'll get a little bit more into that in a second. 9atom also updated for at least V2, I think a little bit beyond that as well. Thereafter, Ninefront starts to work on expanding to 21 bits and getting support throughout all of our software. And I wanted to just mention here, this is ongoing work. We still find bits and pieces of code that doesn't kind of meet our standards for what we would expect. Just this past year, there was some work pushed to Ninefront on allowing Unicode and YAC identifiers. So that's something new. Just saying that this is an ongoing effort. So I want to kind of walk through, how I was using the system, how I kind of found the need for some work to be done with Unicode. As I mentioned, Plan 9's libc includes some kind of rune variants of typical C functions. One of which is, there's the classical kind of Unix ctype.h function. So your two upper, two lower, is lower. Plan 9 extended these, and we have kind of two upper rune and is lower rune and functions like that. I had found that in Ninefront, these functions were never updated for characters above the 16-bit area. So, that 16-bit area has kind of been referred to as the basic multilingual plane. So we were missing anything above that, any other plane besides that BMP. Interestingly enough, when I kind of was doing research for this, I'd found that 9atom did update these functions for at least V2 and I believe also V3. But that work kind of never ended up making its way into Ninefront. So, this is an opportunity. I said, we should go about and fixing this. I will mention the existing implementation before this work started. It was just a big static array of all code points. And we did just a binary search through that big array based on the code point value in question. So to upper rune would take that rune, do a binary search through the big array, and then find the complementing rune in order to, return. So, when we're visiting this stuff, I started to think, Unicode is a evolving standard. It changes every year. It seems like now, it's not always been the case, but seems to be more recently. We get new stuff every year. So it's a treadmill, right? If we're going to write functions that support this interface, then we're going to need to, keep up with the Unicode standard as it evolves and changes. So I started digging into it. Is there some way that we could do code generation based on the information that the Unicode standard provides? Thankfully, the Unicode standard does publish very nice kind of awkable .text files that contain all of the necessary data that you would need for implementing something like this. In fact, the lib Unicode, which is provided as part of the original Plan 9 distribution, was itself a cut down variant of this Unicode data.text. I believe the column differences were changed a bit, and things were converted from uppercase to lowercase. The Unicode standard tends to be a little shouty, I found. So, now we have kind of a plan of attack. We have our Unicode data.text files. We'll write some code, we'll read through the standard, and we'll generate these functions as output. And this should hopefully allow us to, more easily keep up to date as the Unicode standard continues to develop and flourish. When visiting code like this, it's also important to ask the question, can I leave this in a better state than I found it even after updating it? And so it was worth the conversation to decide, hey, can we do something better than this binary search? I mean, the binary search is probably fine, but the number of characters in Unicode is only going to grow over time. So, the impact is going to, the time spent searching is going to increase over time. So the thing about the Unicode kind of code point space is that it's grouped kind of by language, and sometimes things grouped by things other than language. But the point is that it's organized. You have, like characters generally with each other within, kind of that code point space. And for these functions specifically, the to upper and to lower and is upper is lower, not every language has a need for these functions. CGK has no notion of casing. You can't convert a hiragana ideograph to uppercase or lowercase. That's not something you can do. So this kind of creates this, naturally you have kind of parts of the code point space where you have information that you need, and you have large swaths of the code point space where you don't have any mappings. And this kind of creates it's just a property of this data, and we can use this property to design an efficient lookup table that is both, expedient and, moderately sized. And in order to help with this, for specifically these two upper and two lower variants, it becomes advantageous to store not the resulting rune from the operation, but to store the offset, either positive or negative, from that base rune. This not only allows you to store large swaths of zeros in the CGK table space, but also to ensure, like, for example, the ASCII, classic ASCII range, uppercase A and lowercase a are the same difference away from each other as uppercase B and lowercase b. So, this allows, kind of like values in that area as well. So as I was working on this, I was discussing with other people, and Ori had sent me a book called Unicode Demystified. Fantastic read if you're interested in the kind of every detail you could possibly want to know about Unicode. But that book presents this kind of this data structure they call compact arrays. Now, the lookup of it, it's really just page tables. You construct them a bit differently, but really it's kind of just a page table lookup. So you start with, I'll kind of walk through how we build this. We start with a, one-to-one mapping in an array. We have a code point can be 21 bits. So we create an array that has, 21 bits worth of indexable values. You split up this index into equally sized chunks. So, say split everything into 32 values and 32 values and 32 values and 32 values and so on. What we then do is take the end of one chunk and the beginning of the next, and we walk backwards through the first and forwards through the next, looking for similar values. And for every similar value, that allows us to kind of overlay the chunks on top of each other, with the most ideal case being two identical adjacent chunks in which they can be entirely collapsed onto each other. Now, when you do this, you're going to, your one-to-one index no longer works. You no longer have 21 bits of addressable characters in this. So you need kind of an additional array, a higher level index, which allows you to kind of point into the same chunk for different kind of, virtual chunks. So this was that's kind of the basis of it. This is what I ended up going with for implementing a lot of these lookup tables, not all of them, but a fairly large majority. And as it turns out, it becomes advantageous to not just do this once, but to do this twice. So you do this compacting step on your kind of initial data lookup. And then once you have your kind of two layers, and once you have your two layers, you can then perform another compacting step on your kind of index layer. So you end up with kind of three arrays. You use the top one to index the middle one to index the bottom one. So you kind of end up with using kind of three sets of bits from the input for addressing each of them. So in terms of implementation, we have code for reading these .text files, and we're generating these compact arrays. We do these two layers of compacting. I wish I had a more sophisticated way of telling you how I picked how many bits were assigned to each of these tables, but it was trivial enough to brute force these and find the smallest generated table. So that's what I did. So, for the two upper, two lower, two title, I found that using 10 bits for the layer 2 index, 7 bits for the layer 1 index, and 4 bits for the bottom kind of data chunk layer seemed to kind of do the trick. For the is tables, the is upper, is lower, we used one single table that was filled with bit vectors. One bit was assigned one specific category that Unicode had assigned to that character. So we're kind of able to smush that all together. So that data table is a little bit more dense. There's not large swaths of zeros in that one. And for that, we had kind of it was pretty similar, just kind of 1 bit difference. We used 11 bits for the layer 2 index and 6 bits for the layer 1 index, and that same 4 bits for that bottom level chunk offset. So this is kind of our initial results from doing this. So our 2 upper, 2 lower, 2 title, it was we had just a little bit over 10K for each, and our combined is rune table was a little shy of 25K. So all in all, if you're using all of these functions, you're paying just about 60K worth of program size for having a constant time lookup for kind of all of these types of transformations, which to me that seemed well worth the expense. So what can we do next? Well, we now have this tool. We can parse these Unicode standard database files. We can generate these efficient lookup tables. What's the next, natural next thing that we want to do? And to me, I really wanted to kind of tackle this normalization problem. We have these data tables now. This is a more complex operation that we're allowed to do. And I also looked for some freebies. What are some easy algorithms that we can implement now that we have these tables? Turns out like both grapheme breaks and word breaks are fairly trivial algorithms given you have the correct data tables. So those kind of came for free. These were an additional kind of, we have the tools, let's get that implemented. So before we go into kind of how normalization is implemented, I want to make sure we're kind of on the same page as to what Unicode normalization is and why it's necessary. So Unicode, for both historical and design reasons, has two ways to represent some types of characters. So we see in this example here, we have our kind of our uppercase U with this diacritical marking here. And we also have, the same character, visually to the user represented here, where the first variant is there is a specific code point assigned to just this specific combination of uppercase U with this specific diacritical marking. In the other case, this, 55, this is our ASCII uppercase U that we've all come to know and love. And then this is a conjoining code point. This code point says to attach this specific diacritical marking to the character that is, the base character before me. So, these are, the standard has both of these variants, and this creates a problem, right? As a user, without knowing some of this context, you're seeing the same character. You're trying to log into a website, you're trying to open a file, and you're typing what you see on the screen, but the computer is telling you, no, I don't have a file, I don't have a user with that specific string of bytes, that you've given me. So this creates issues where you have kind of difference between what the user's perceiving and what the computer is comparing. So for the purpose of providing a better semantic comparisons, we need some way of converting any sort of text consistently into one form or the other. For this purpose, the Unicode standard defines two forms, so technically four, but the other two, they're not very important. We define, for this purpose, we care about NFD and NFC, normalization form decomposed, normalization form composed. So in NFD, everything that can be decomposed, everything that has multiple that can be broken out into multiple code points is. Whereas the NFC is the inverse. Anything that can be recomposed, anything that can be used, represented using a specific tailored code point is used. Now, when you normalize to NFC, not everything is guaranteed to be composed. There are certain characters that only have can only be rendered in decomposed form. It's a bit of a gotcha, but that's a bit besides the point. Now, the algorithm which turns input text into one form or the other, that's normalization. So that's kind of what we're talking about here. So, like I said, we need some data tables. Let's talk about the data tables that we need. For starters, we need to be able to map either the composed rune into its two decomposed counterparts, and need to do the inverse. We need to map the two decomposed runes into its pre-composed counterpart. Now, Unicode always defines decomposition to be 1 to 2 or 2 to 1. But however, you can have multiple layers of decomposition. So I believe for one part of the algorithm, I needed to kind of find out and write code that figures out how many chains of decomposition can you go through before you're done. I believe it was 5. One character can be decomposed 5 separate times. So just keep that in the back of your head. Now, in addition to these two kind of, rune mappings, we also need the combining character class. This is important because when you have decomposed Unicode, to the user, say instead of having just one combining character diacritic, we have 2 or 3. This is common in languages like Vietnamese. You need a consistent ordering of these decomposed characters in order to compare semantically across multiple variants of decomposed Unicode. The property of these code points, which stipulates how these are sorted, that's the combining character class. So we need this table as well. And we're also going to be needing this quick check value. This is used to kind of solve an edge case that's present in some of the chunking that we'll do later. I'll talk more about that in just a second. Conceptually, though, quick check is a pre-computed value detailing if a character is allowed in a certain form. So, for example, this specific U with combining diacritic as one code point, quick check would say, nope, not allowed in decomposed form. Similarly, something like this combinational right here, it would say, nope, not allowed in NFC. That's so that's what that quick check table is providing for us. So both the quick check table and the combining character class are fairly easy to implement. They look very similar to our existing tables. They are implemented just as compact arrays like everything else. And we pay about, roughly 10K for each, not too bad. However, the decomposition and recomposition tables, these require a little bit more engineering, specifically because we're dealing with we have to deal with multiple sets of runes, potentially 42 bits. Realistically, you're rounding that up to 32-bit words. But, let's see what can we do to kind of reduce that space sent. It turns out that for both decomposition and recomposition, there's a heavy bias for valid code points to be in the basic multilingual plane, in that 16-bit code point space. So for decomposition specifically, we also have, our input's the same as our other compact arrays. We have one 21-bit rune as input. Our output is just the two runes. We're going 1 to 2. So if we know that our outputs are very likely to be in that 16-bit basic multilingual plane, we can just smush them together into one 32-bit integer for our value for our tables. And this ends up working quite well. It's tenable to use compact array for this. But what do we do for code points that are above that basic multilingual plane? There's not many of them. At the time that I had done this implementation, there was 158 code points that resulted in results above the basic multilingual plane. So for this, I kind of carved out a little set of the Unicode private space. When processing this text, it would be impossible for a normalization, a decomposition, to produce anything in the private range that's not allowed. So we cut a little bit out of it here to stash our extra 150-bit code points. And what we do is when you're decomposing one of these candidates, which produce one of these larger code points, we produce instead an offset from this base 0xEEE, E for exception. Beginning, and that is then used to index just a flat array that has the answer. So we just kind of tack on an extra, hey, it's only 158 runes. We'll just tack that on at the end. And this allows us to kind of maintain this constant time lookup. We may be reaching into two different tables, but it's still, we get our result from the first table. We know exactly what our offset is into the second table. We don't have to do any searching. Now, recomposition is a little bit more involved. So we do have that same bias, the basic multilingual plane. And, in this case, we're taking two 16-bit characters in the ideal case and outputting one 21-bit character. And as you saw earlier when I talked about kind of what bit value ended up working well, surprisingly, the large kind of chunk of a lot of these compact arrays were the actual index tables themselves. And extending that index table to not be 21 bits, but to be 32 bits, it blew up the size quite considerably to the point that it was worth exploring other data structures that we could use to implement this. So, we still want near constant time lookup. So, let's try a hash table, let's field it out. So I came up with this kind of, this is our hash table struct we'd use. We have our kind of our U32 int key, so our two kind of basic multilingual plane code points smushed together. And we have one basic multilingual plane output, that's our value. And next we'll talk about that's for collisions. Now, a little bit of a trick here is we need to kind of serialize this out to one big block of memory. Remember, we're doing code generation here. We can't have pointers that point to different parts of memory. It can't look like, a simplistic implementation of a hash table. So it's not too bad, though. We take kind of our initial buckets, our initial set of NKVs, and just write them out as raw bytes, which we can do as two uint32. So one for the key, the next is, again, that value and next kind of being smushed together. As for the collisions, we simply store them as an amendum to the kind of back end of our initial buckets. And that's where the next value comes in. The next value points to the absolute offset from the beginning of the collision space, where to find the next element in the kind of the collision list. So that works out pretty well. We can keep everything in this one big block of memory. I did search around. I tried pretty hard to find a hashing algorithm that provided some decent enough results. What I ended up with, again, at the time for version 16 was 512 initial buckets, which gave us about 555 collisions. So we had 555 exceptions. So, on average case, you're probably looking at about 1 to 2 collisions per entry. It's not too bad. I mean, it's a little bit more work than our compact arrays, but not by much. We're still, for these basic multilingual plane code points, we're still doing this in constant time. However, what do we do for code points that are above the BMP? Well, there's really not many of them. Unicode it's a little bit funny in that there's more decompositions than recompositions. While the Unicode standard states that they don't have a preference for one form or the other, there is a soft bias towards decomposed variants. So you have singleton decompositions and decompositions that work one way but not the other. So for recompositions, the amount of code points you have that kind of break this basic multilingual plane are under 40. I believe there are 37 or 38 in V16. So for the time being, we have that exception array. If we see an input that is greater than 21 or greater than 16 bits, we just search this list linearly. There's like 30 of them. It could be done more effectively, but I haven't seen a huge impact so far. So could be better, but for now, with the limited number of them, not a huge deal. So how'd we do? What's our table sizes? The decomposition table ends up being a little bit larger. We're just a little tiny bit over 20K. And our recomposition table ends up actually being quite small in comparison. Again, a little bit more work for the lookups. And, we do have that exception table. But in total, 30K for having, every decomposition and recomposition mapping in largely constant time, save for a couple of edge cases, is fairly nice. So now let's actually talk about, how do we implement, the theory? We have our data tables ready to start actually implementing normalization. So the standard is a bit deceptive. It kind of explains things in these very abstract terms. It says, for normalization, all you do is you decompose everything, you sort the conjoiners by their combining character class, and then you recompose everything. That last step, that recompose everything, that's the difference between NFD and NFC. So if you're normalizing to decomposed form, you just decompose everything and sort. And then you'd also do that if you're normalizing to the composed form, but then walk through and put everything back together again. This everything bit is the kicker. As I mentioned earlier, you can have multiple chains of decomposition. So implementing this abstractly, as they suggest, you're going to be doing multiple passes through the entire string. This won't do. We can't, you can't build a streaming interface like this. We don't have infinite RAM. We have to find a way around limiting the amount of memory used for processing a single portion of the string at a time. So what you really want is to be able to take some string, start reading it, and build a context, build a stack. And then when process that individually, and then when you're done with it, you want the freedom to flush that out. So we can work kind of with a fixed amount of memory at a time. So for chunking, this is kind of the chunking method that I came up with. The Unicode standard's a bit clammy about how you're supposed to actually go about doing this. I find it a bit frustrating. This is what I was able to piece together was through a bit of trial and error, a bit of understanding about how the code points actually decompose and recompose with each other, but there may be some theoretical inaccuracies, but as we'll see earlier, this is a tested implementation. So broadly, you have two types of context. You have your first case where you have your base rune and your conjoiners. So that's kind of like that earlier example that I gave with the diacritical markings, where you have your kind of ASCII U and maybe 3 or 4 or 1 diacritical markings. This context is fairly easy to extend to. You simply continue to pull stuff onto your stack until you hit the beginning of the next context, until you hit the next base rune. You can tell this based on that combining character class, as I said. Base runes all have a combining character class of 0. So this is a nice while loop. You keep pulling stuff onto your stack until we hit a combining character class of 0. Not too bad. However, there's a second type of context, which is where you have code points that are made up of multiple individual pieces, but all of those individual pieces themselves are base runes. So this happens in Korean Hangul. You have each of the Hangul characters are composed out of multiple individual pieces. Those individual pieces are not conjoiners. They're their own characters in their own right. And this is a lot harder. I couldn't find a good answer as to how do I know when I'm finished with one and started the other. And this was something that actually had to be changed between version, this code was initially written against the version 15 of the standard and then updated to version 16. In version 15, the only case of this was Korean Hangul. You could special case just Korean text and handle that entirely fine. Unicode version 16 added another language that also has these properties, so this had to be generalized. What I found, what seemed to work, was to use that quick check value, as I mentioned earlier. So we just grow context until we hit a boundary, and we define this boundary as a quick check, saying it belongs in the form with certainty. The quick check values have two potential values. You either have a no or a maybe. They don't give you a yes. A yes is the lack of no or a maybe. So we walk until we know for certainty that what we're looking at belongs in this specific context, and then we take everything that we have so far. This is a bit greedy. It takes a little bit, the context grows a little bit larger than it might necessarily mean to, but this is the best way that I found to kind of generalize this problem. So with that said, we have, there's some more edge cases. Unicode does not specify a maximum number of conjoiners that you can have to a base rune. They say you can have as many as you want. Unfortunately, computers don't have infinite RAM. We need some limit. So a subset exists. Unicode does define this kind of variant called stream safe text, where they say, okay, look, you get 30 conjoiners. No actual natural language is going to ever use this many, but that's the limit that we're putting on it. I imagine the idea is you have 30 conjoiners plus 1 base rune plus 1 null terminator fits in a nice even 32 bytes. Now, what do you do then if you're processing text and you get, 1 base U with 200 combining diacritical markings? Well, you have to, you're permitted to insert a new rune into the output, this combining grapheme joiner, Unicode .34f. And this acts as a intermediary base rune. And so we implement this as part of our normalization. And the reason why we need this is a little bit subtle. Remember earlier I mentioned decomposed conjoiners have to be sorted by their combining character class. Now, in order to sort the combining character classes, you need to have all of them in one array. You need to kind of be able to bring the first element all the way to the end if need be. And so if we allow that context to continue to grow infinitely, we run into problems. So the combining grapheme joiner, by acting as an intermediary base, it allows us to sort the conjoiners in chunks. So we can sort the first 30 conjoiners and put them on the actual base rune, then take the next 30 conjoiners, sort them as for the combining grapheme joiner. And that's kind of the reason why this is necessitated for kind of implementing this within bounded memory. So we have we now have our implementation. How are we going to expose this to other programs? What's our library interface? We came up with kind of one state struct and two kind of base functions. You have one for initialization, and in this initialization, it takes in an existing state struct. It takes in a flag that specifies either we're normalizing to NFC if compose is greater than 0, or we're normalizing to NFD if compose is equal to 0. Context is whatever user supplied pointer they would like, and that is then kind of preserved and sent over to getRune, which is a callback that the kind of normalization algorithm calls to in order to grab more input runes depending on what it needs for the context. So you do that, you give it the function pointer, it starts pulling runes in. How do you start pulling runes out? Well, we have this norm pull function, which again takes that same state struct, takes a destination for where you would like to store the output, takes the size of the output, and then we have this flush argument. This one's a little bit tricky and a little bit annoying. So remember, as I mentioned, you have to continue to grow context until you see the beginning of the next context. So if we just see a base rune and we're doing the streaming interface, we do not know if, hey, the next rune could be a conjoiner, the next rune could be another base rune. We don't know yet because we haven't seen it. So we need to kind of keep one context buffered in the state struct until we know for certainty either we're getting more text or there's nothing left. This flush argument is what allows the caller to pass that information to the algorithm. So if you have 10 bytes, you give it all to the normalization algorithm and you're like, I'm done, there's nothing more, bar's closed, go home, you pass flush, and that kind of gets that last bit of context out of the normalization implementation. So we decided that streaming is kind of the more complex of the two between fixed interfaces and the streaming interface. So we did implement, fixed sized input interfaces as well, but these are all implemented using the streaming interface. And so we just have, rune comp and rune decomp. These are just NFC, NFD. We provide both rune and UTF variants for convenience. And these work, more or less, it's the same algorithm, just a different interface for it. It is worth noting, though, that if you do not have enough space in your output, because, normalization can expand the amount of characters or contract it. So, if you do not have enough space in your output is truncated. The kind of ideal caller for these functions was, hey, I have some standard. Standard says I have 256 bytes to work with for this, or 256 characters. I need to normalize it, but I know the output is going to be limited to 256 6 bytes. So that's what you would use this for. So the Unicode standard is nice enough to publish tests for us. The tests are fairly extensive, a couple tens of thousands of test cases. Very nice that they do this. This implementation was written against these tests. It was considered done once we had passed all of the tests presented to us. And being able to bring these tests in was super useful. It helped identify the issues when upgrading between version 15 and version 16. So that was a huge win. And in addition to kind of the standard published tests, we also have some tests of our own, which are more testing the interface. So testing that the combining grapheme joiner is inserted correctly, checking that we're, breaking conjoiners up at the right offset and stuff like that. And there's a couple of edge cases with there. It ends up you actually have a conjoiner which itself can be decomposed. So you can wind up in weird scenarios with that. It's an interesting edge case. So, we have this now. How is this used so far? Well, initially we have support now in Ninefront's TCS. So TCS can now convert input text into both NFC and NFD. So you can perform normalization on both a pipe input and file input. Likewise, Street Lisp, a Lisp that's being developed by Sigrid, has also been vendoring this implementation of normalization for the languages support for normalization on all platforms. So everything, they kind of took this implementation and are using it everywhere. So remember, I if you can remember, I talked about this a ways back, but we do also get a little bit of some extras here. These were easy to implement. So the grapheme break and word break, these dictate kind of where one logical character to the user, so whether it be one pre-composed character or one base rune and decomposed conjoiners, it defines the beginning of the next base rune. This is different to normalization. That part is also part of normalization. No, these functions don't use each other. It's its own thing. So this was easy enough. I believe the implementation is like 60 or 70 lines of code once you have the tables. So these were easy enough to add. Likewise, word break too, that finds breaks between sets of words and long streams of text. And for these, we had, again, 2 implementations, rune grapheme break, rune word break, same with UTF, and they just return the pointer starting the beginning of the next context. So where to next? What's the next step in increasing Unicode compliance within the system? Well, now we can logically handle decomposed Unicode now. We have the tools necessary in order to do that. The issue that we have now is our graphical user interfaces. Things don't handle decomposed Unicode very well. Our font system cannot handle it. It has this assumption that one code point is one character. Our user interface programs, Acme, SAM, Rio, these also have the same assumption. One code point is one character. That needs to change, whether that be a new lib frame, whether that be modifications to the existing one. That's still kind of something that needs to be researched. Also, it's not like there's the question as to exactly how to handle these cases. This isn't an agreed upon science either. Different languages may prefer different things. For example, I have a decomposed code point. If I hit backspace on my keyboard, am I expecting it to delete one conjoiner, or am I expecting it to delete the entire character with the conjoiners? And different people may have different expectations. So, finding out what the correct answer is for us is going to be, might be something that we have to kind of deal with. And yeah, I believe that's the last slide. So thank you very much. I hope you enjoyed this talk.
Yeah, thank you too. It was a bit long though, so we will have to keep questions and answers a bit short. And I will start with one that came up on the internet. And the question is about regexp. There is some special things like words, right? So \w or \b or white space \s. Are you also planning for doing something in that space so that you can recognize the Unicode with regular expressions? I'm aware, for example, of there is a vertical tab character which is white space, but not just a normal space.
That's been discussed. I don't believe none of the discussions that have come out with something that people have kind of been excited about to implement so far. So that's still in discussion. I believe there's a desire for doing something regarding that, but exactly what form it takes is at this point not something that we know.
All right, thanks. Do we got any other questions? Then please queue up at the microphone. Anthony is coming.
This looks like an amazing amount of tedious work, so thank you. I don't know if you've seen it, but Eric Quanstrom did a bunch of stuff with grep for sort of the Unicode version of case folding that might be relevant for this.
Oh, interesting. I must have missed that when I poked through 9 at him. Yeah, I'll have to take a look. Thank you.
It was significantly later than the original, the like 21-bit thing.
Okay.
And there were several points where you were describing things like the 5 layers of decomposition where I just started laughing. And I'm curious if you have an example of something where you can do the decomposition in one direction and can't put it back together.
Yes. So there are singleton decompositions. So you can have one code point which decomposes to one other code point, which the Unicode consortium has abused for trying to hide their dirty laundry in the closet of legacy code points. Singleton recompositions are blanketly banned. You cannot recompose one code point back into one code point. So that's one class of can go one way but not back the other.
Are there any other major Unicode algorithms that we'll probably need to be implementing in the future?
For doing this kind of logic stuff, there's line breaks. We may or may not want that. Grapheme break and word break can be useful in terms of like implementing editors. Line break is much more of like a typesetting kind of property. Not that I was aware of initially. But for stuff like rendering stuff, there is that text shaping and stuff like that, whether technically maybe Unicode algorithm or not, that's kind of a whole other thing that is kind of a big to do so far. There's other stuff we might need. But if there is other stuff people would like, send me an email, we can talk about it.
All right, that's it for questions. So yeah, thank you very, very much. And we will also make sure that you also get a nice, cute little 3D printed Blender to your house. Thank you.
Oh, fantastic. Thank you so much, everyone. See ya.
Okay, and you will change the slides when I ask. Yeah, great. Okay, hello. My name is Fredrik Stromberg. long story short, I enjoy building, designing, building, and trustworthy systems in both hardware and software. I've been interested in cybersecurity for 25 years, and 15 years ago I started a company, and now there are multiple. The one I started is called Mullvad VPN, and now we do other things too. Next. Okay, why do we like computers, or why are they useful, economically and societally useful? It's because they automate behavior that used to be done by humans. But computers don't need food, they don't need, they don't get bored, they don't need to sleep, and so we like to automate things with machines, and that's what Turing came up with. Next. Unfortunately, with increasing task complexity, the intended behavior of the person you are asking to do something, and the expected behavior, intended behavior, and the actual behavior, they diverge. It's the same with computers. If your design is complex, what you described in HDL or in source code is unlikely to be what you actually expect when it's running. So the delta, with increasing complexity, these lines diverge, and the difference between intended behavior of the system and the actual behavior of the system is your bugs, your vulnerabilities, and your attack surface. Next. Okay. And so we can describe this in a few different ways. We have some human, a computer with the job title of computer in the 1930s, did some behavior, and now instead we have hardware. Unfortunately, we can't build chips that behave exactly as the thing we want because it's too expensive and impractical, and so we want programmable hardware. But that's not enough either. We also want to know that it's my computer and my software, and so we need an identity connected to the hardware and to the software. Next. And I have a short list of things that I find the most useful when I design things. These are the ones. I don't have time to go into why, but I like strategy, I like heuristics, and if I had to compile a short list of things that I try to use again and again, and that I use to evaluate whether a system is trustworthy or not, these are the things I use. Next. One of the things I've designed is, together with colleagues, is a open source hardware USB security key. It's FPGA based. You can go to telitis.se and check it out. More or less everything is open source. Schematics, PCB design, HDL, firmware, software, tooling, and build system. There's a RV32 ICZMMUL ISA on there from the Pico RV32 soft core. 128 kilobytes of memory for the device applications. There's a TRNG, and one of the important things about it is that you use a KDF and measured boot to create unique key material for the thing that you upload. So it's basically a trusted execution environment on a USB stick. Next. This is a thing that I'm working on right now. It's a type of HSM. The inspiration for this one is the USB Armory, the Cryptic HSM, the T-key, and a few other things. The idea with this one is that not only do we measure the software, we also measure the bit stream. So we have key material that is based on the hash of the bit stream that we upload onto the Lattice ECP5 FPGA. So on the host, we connect the HSM to the host over USB. On the IMX6, we'll have Tamago running. And then we send the bit stream to an ICE40. That's what we use for the T-key right now. Which measures the bit stream, configures it onto the ECP5, and then we have a nice, very open source hardware HSM. It turns out you can hash hardware. Next. I don't have time to explain what the transparency log with distributed trust assumptions is, but I worked on it for 4 years with colleagues of mine. The cryptography that we designed into the co-signing witnessing is now used by Google's transparency logs as well. And it's very likely to become a global cryptographically compatible standard. Next. And these are some other things that might interest the Plan 9 community. Tamago can now be used on x86 64 VMs and on bare metal, booted by UEFI. That's a thing that I funded, or my company's funded. On my wish list for things that someone should do would be to do inter-VM shared memory as a transport for VirtIO in Linux, because that would simplify or enable using Linux VMs as driver VMs for cubes like... done. Sorry. No questions. Bye.
Bring your own laptop? Okay, good to know.
Yeah.
Exploiting ShareHub. The suggested topics included security, so I decided I would try my skills exploiting ShareHub. And apparently, can I exploit it live, or is it's all right? It's easy to fix, so yeah. So apparently, there is this ShareHub site which is great and works fine. But if I look inside, I can see that the get rules file contains some quoting somewhere, but does not contain the quoting in the other place. So if we do this and this and this, we can see the current date. Yeah, we can also put a funny message on the front side. Arusek was here. In the yeah, it's just the cached version. Thanks.
So I'm Emery Hemingway. I'm going to demonstrate some content address file systems on Ninefront. A couple years ago, I was funded by NLnet to work on Eris, which was a standard for sharing data between applications, funded by NLnet. And this was a breakout standard out of a few different projects, a couple of projects that went nowhere, but this was something we wanted. So it's inspired by the capability security model. So you have identifiers that look like this. This is a bunch of base 32, and in there you have a Blake 2B256 hash and a cha-cha 20 key, and you use the hash to grab a block, and you use the key to decrypt the block. And I did the Go implementation, and so it was obvious to me, do a 9P server. So here, this is how I start the 9P server. I give it the address of the host, and then I give it a cache directory. And then I added support into 9FS, so I can just mount these URNs. Sends the URN over to the 9P server, and the server loads the file system structure out. And then you can see there should be a bit of network traffic. And in this case, I'm just loading a directory of images. And then over here, I have a cache directory. And you can see that it's just storing blocks on the file system. And the blocks on the file system are encrypted. So you're fetching encrypted blocks over the network, but then there's this transparent decryption that happens. So yeah, in this case, the decryption is happening inside the 9P server, but it's not logging anything. So basically, and it's a private mount. So here, the page client, if I close this window, kind of the server doesn't retain the keys that are used to unlock or sort of decrypt the blocks. And like comics are a good example for a presentation because it's graphical, but it works really well for like a music folder because you can kind of have this cache of music that you just lazy load. But I'll stop there.
The image comes up. So HP has put these about 5 or 6 modern multi-core servers online, and if the network were working, I could show you the login. But you have the option of loading the VMC, the server firmware, but more importantly, an ISO with your image on it. And they are in the process of putting the latest Ninefront ISO as an image you can select to boot. So this is a good chance to try and get in there and make sure that you know, your kernel works on fairly modern server hardware from HPE. So osfci.tech. It's a very simple sort of login process. If you don't remember that name, come and see me about it again. osfci.tech, that number. Huh? Open source, open system firmware. It's the thing I started long ago, and it's all about, you know, making the firmware open and writable. And Jean-Marie Verdun at HPE set this thing up, and amazingly, it hasn't been taken down by anyone. There you are.
Alexis, let's see if I can get the screen up. Anything?
Are you giving output on HMI?
I hope so. But maybe not.
It's very dark.
Then I'm not sure how to operate.
You're sharing a black screen, it works.
Nope, then I can't present. Not sure how to put this over to a different screen. It's an XOS.
Oh, I'm sorry for you.
How are you trying to do this?
Try Arch.
I thought it would just mirror.
Just do xrender -- auto. XRANDR.
more about Nix packages and how to run Ninefront fairly easily. So here I have a Nix flake, and what this does is for the different architectures, it downloads the different QCow images that are pre-built, and then Flake just creates a few shell scripts that will run the QEMU with the downloaded images, and it has a little bit of scripting in there, which is right here. So what this does is when the VM comes up, there's a little bit of an expect script that will just set up a local user and enter that to factotum. And there's different outputs in a Flake file, and one of these outputs is also draw term. So to display this easily, I'm just going to do run nix hash Ninefront run. And you're not going to see everything. Not sure how to make this maybe a little bit smaller. And now you can see that this is sort of already scripted with the expect script, so that we have a serial console. Thanks to Mia for that. And then it sets up the boot, starting HFS. This takes a while now. There's a term prompt, and now it's doing ipconfig, so I'm just sure that the network is set up. Let's see if I can do this even smaller. Or maybe this way. There we go. All right, so it takes a little while. Please bear with me. So it's set up a new user, and the shell script is already a little bit configurable, so you could do a different username or a different password. And now it starts the server. And then if I switch to a different terminal, like this, I hope. Okay, I'm just going to do it like this. Yep. And I do, so I'm in the same directory with the same Flake file, and I do draw term run. Then this again is just a shell script that builds draw term and then issues the necessary commands, and something that you unfortunately cannot see yet. Wait just a second. So now here we have draw term that's running. And if I enter the password, then I have plan 9. And the nice thing here is that, for example, the Flake file already uses a Linux cross builder on Darwin, for example. So the whole setup also works on Darwin. And it uses U-boot and the Nix packages cross-platform builder to build U-boot and inject the U-boot into the QEMU as a bootloader. So everything is just contained in that one Flake file. And it builds on x86 Linux if you have Nix packages, or even on Darwin. So it's fairly easy for folks using Nix packages to run Ninefront through draw time. Thanks so much.
Okay, so my name is Roman, and this is very much an impromptu sort of announcement motivated by the talk done by Paul, and I guess the work done by Paul and some of the folks on the like Ron and some of the folks on the Nix side. So apparently there is some interest in the type of the architecture, hardware architecture that Esperanto was building. So we are now sort of taking over that and trying to turn it into the open source many core architecture. Again, very much along the lines of what got presented. We have a fairly good idea of what we're building on the hardware side, with, again, a lot of ideas of how to scale it from, a couple hundred cores to a couple thousand cores on a chip. we're exploring all sorts of ideas on the software side, and how that type of a system should be orchestrated and organized in terms of what runs on each individual core, and what kind of workloads we can do. So if you have interest in any of that, talk to me. I'll be around here, or to me or my co-founder, and that's basically it.
The basis is it's like Tailscale but for 9p. That is that you do the so IoT world, they're trying to do REST. None of it is really secure. You still have to come up with conventions and have the namespace exposed through REST. So trying to, if you want to have a sane way of controlling remote devices, you establish through REST, and now you got to run a little web server on this unsecured IoT device, et cetera, right? And you're still trying to create some sort of a hierarchy that starts with HTTPS, or hopefully. But the idea is to essentially have everything client initiated or endpoint initiated, edge initiated. Most of those, at least in, let's say, using embed TLS, for example, they do support TLS 1.1, 1.2. Not great, but if it's edge initiated to a central point with key exchanges, you can sort of, or we're pre-shared, essentially keys, you can have some guarantee that you can verify that the client is connecting to the central server where you have more control, is at least generally who they say they are. And then once that client connects, you establish the 9p connection. And the 9p connection at that point, the client side becomes the file server. And then you start serving the namespace of whatever device your PyPico is controlling a bunch of relays. You're exposing that as a file system, and the central point then can mount those or expose them to other entities down the line. So the other part of this is that central point is both for identity verification as of the edge devices, but also for users that own those edge devices. And that central point, so that would be for the end users, would be through things like OpenID Connect. That central point can also then act as the stun turn. They essentially use Tailscale's derp server. And now you can do the hole punching through NATs, and Bob's your uncle, and that's it. All we need now is some code. It's done. It's already done.
Yes. So maybe you remember a program, a technical report from Bell Labs on the Blit, I guess, talking about crabs like small. So I found that funny, and I just re-implemented them on Inferno. So basically, because you have access to the whole screen, and there is no like on Linux notion of Windows or whatever, it's just bits and so just you have little entities, and if they get a dark pixel, they eat and they reproduce, and you get new ones, and they do a random walk, and they can like eat your screen and eat one another and so on. And if you can trigger a redraw, then because they see if they've been wounded, so if you can trigger a redraw fast enough, they will die and leave you alone. But if you can't, then they will become too numerous and like eat your whole screen. So if I move this window, they will all die at the same time because it will redraw the whole window. But for example, if they reach this part of the screen, then you are done because you cannot redraw this part and so on. So you can have some fun, and then you can imagine like multiple species eating one another and so on. And it's like 200 lines of limbo, and it's we can play with it tomorrow if you want.
Okay, we good? Recursive make sucks. So I've been starting to do a little bit of work on fixing that. Basically, the very short summary of that is, what if you could include a muck file from a subdirectory that knew about where it was being included from, so that all the rules would run in that subdirectory. That basically cleans up a ton of stuff in the build system and lets you depend on rules from outside of your current directory, and you can actually build things correctly. I've got the initial bits of it working, and now I need to actually namespace the environment variables and the rules so that you can actually look things up correctly. Because I didn't want to bother futzing with the laptop, and I only have 2 minutes anyways, I'm going to just quickly draw what that looks like on the board and what it will end up looking like for cross-directory dependencies. Sorry for the people online who will not be able to read the writing. Your obj type thing, which is a context-free one, you set up your rules, and then you do the one that knows where it's at. And then you can depend on, sorry, you dear at, let's go with a concrete example. cc at libcc dot a dollars. Oh, and now you can, actually, percent dot dollars o depends on your libcc from your, I guess, dot/cc. And now you can start including files across your entire source tree. They'll get built correctly. They'll get built in parallel, and you get rid of a lot of mess in the whole let's cd and run a new muck.
All right, then that concludes today. To everyone online, thank you very much for watching, and I'm terribly sorry for any of the audio, Wi-Fi, and whatever mess that we had. As usual, we will try to do better next time, and yeah, see you next time in person, I hope. Ron has a few words to say. All right, I will hand over to Ron, and Edouard, and whoever else.
Yeah.
Through all day, you gave Glenda to speakers. So I think it's your turn to have something in your hands from ours.
Oh. Well, we just wanted to recognize the fact that you have done an incredible job for 3 years in a row on managing all this video, audio, networking, and total hell. And so we have this kind of book of cool inventions from this museum, and then this. If you want, you can unwind the poster, but I think the poster, the poster has an image that's evocative of the complexity of setting up all this audio stuff and all the problems that occur. So I can't thank you enough, Daniel, for what you've done here and made this conference work. So.
And to tie it to Plan 9, the author of the postcards is named Lapin, which is like French for bunny. At the back, you'll see that. Anyway, so Glenda,
rabbit.
yeah, exactly.
Yeah.
Bunny, rabbit, same difference. Anyway.